Hello, everyone. Welcome to the 13th SurrealDB live stream, if you can believe it. I had a little bit of a break, over half a year, but we'll continue. So, today's topic is basically researching full text and vector search. That's the main idea. I have an idea for little like search as a service app slash SaaS for like very low very low cost, very low, very small website thing, whatever. And I figured that this would be perfect opportunity to look at the capabilities of search through SurrealDB. So without any further ado, let's just jump in and we'll see how far we can get today and what we'll actually cover, because I don't have much of a background on the topic. Okay. Let me just make sure that everything works. Looks like it might. Okay. All right. So let's go to SurrealDB and we should have something about it. Some docs, right? Resources, documentation. Let's look at just SurrealDB docs without going to query language yet. And looks like I need to change the little thing on the bottom. Full text search and vector search SurrealDB. There we go. Not that anybody sees that. Alrighty. So SurrealDB, we have topics, data models, we have vector and full text search. Look at that. So let's look at full text search. Full text search database that is designed to make building and scaling real-time apps dramatically quicker and easier. So yeah, we'll be doing lots of reading today. I want to kind of figure out what I'm dealing with, what's possible, and how much effort it takes. Using SurrealDB as full-text search database. A full-text search database is designed to index and retrieve text-based data, like articles, messages, or comments, based on the meaning and structure of the text itself, rather than exact literal matches. This allows to find documents containing certain keywords, search for phrases or words with variants, for example, run, runs, running, and rank results by relevance, not just by literal string matches. Exactly. Traditional relational databases have some limited text search capabilities, with varying degrees of support for text indexes. But more specialized systems like Elasticsearch or Lucene-based solutions excel at performing complex, scalable full-text queries. Exactly. As a new multimodal database, SurrealDB has developed integrated full-text search capabilities so that you can store your data as documents, graphs, or tables, and query it with advanced text search features. This guide will explain how to think in a full-text search model and show how SurrealDB helps you implement these concepts seamlessly. Perfect. So, core concepts of full-text search. So, all right, looks like we're going to learn some keywords. That's good. So, we have analyzers. In a robust full-text search system, analyzers define how the text is processed. An analyzer typically includes tokenizers, which split text, and filters, which modify tokens. Different languages or data types need different analyzers. Okay. So basically, this is how it splits the text so that it's searchable, and all the fun stuff. And I guess different languages will have different analyzers because, in English, you split words in a certain way. And let's say Polish language, you would split words completely differently to like reuse them. You form plural versions differently. You have different prefixes and all this fun stuff. Tokenization. Okay, so tokenizers are part of analyzers, right? So tokenization splits text into smaller units, tokens. I guess now everyone's familiar with tokens due to LLMs and them using tokens, right? Depending on your use case, tokens may be entire words, word stems, or even n-grams. For example, tokenizing the sentence, the quick brown fox, might produce the quick brown and fox, right? But maybe in some other cases, the quick would be split into other things, right? Okay, that makes sense. Therefore, we can search easily by keywords. Filtering. After splitting text into tokens, these tokens can be converted to lowercase, stripped of punctuation, or transformed. For example, removing accents. Additional filters can include stemming or lemmatization, which reduce words to a base form, for example, from running to run. Yeah, because we don't need to hold the text, at least for this full text search. We don't really want to hold the text fully exactly as it is. If we can have like reusable pieces, yeah, why not? Search could be done probably faster. And I wonder if it's possible to already at this stage correct some of the like misspellings or something. Just an idea. Hey Taras, how are you doing? Indexing. Full-text search engines build specialized data structures, things like inverted indexes, suffix arrays, etc., to let you quickly locate documents containing certain tokens. These indexes often store frequency, position, and other details that enable relevance scoring. Okay. So I recall from just overall query language that there are some specific indexes you can create for specific, full text search, and there are probably different ways to optimize them. Ranking and scoring. Once matches are found and a full text search engine ranks them to show the most relevant results first. Algorithms such as BM25 and TF-IDF look at how often terms appear in a document, or whether those terms appear in the title versus the body, etc. Okay. And then we have highlighting. A good search experience shows where in the text the matches occur, often by wrapping matched terms in HTML tags or otherwise emphasizing them. Okay. So we've got some terms, and Tara says, I'm about to start printing. Happy printing. I remember when I started 3D printing, whenever print started was exciting, and often still is, especially when you start printing designing your own models and you start seeing them appear in real life. It's a cool feeling. Alrighty. How full text search differs from keyword matching. Exactly. In traditional databases, you might do something like select everything from articles where the word fox is in the title, right? This approach doesn't rank results by relevance. They just return every article containing fox. Ignores language variations, for example, foxes or FOX or synonyms like vixen. Tends to scan entire columns, making it slower for large datasets. Yeah. Full-text search, by contrast, uses an inverted index or other specialized structures for fast lookups and can handle a variety of linguistic transformations. It can highlight results and rank them by how relevant or frequent the terms are. Okay, so it's way smarter, basically. Okay. Great. SurrealDB as a full-text search database. SurrealDB combines multimodal data storage, document, graph, vector, etc. with an integrated full-text search engine. This means you can store your text in a SurrealDB table or document. Define analyzers that specify how SurrealDB will tokenize and filter your text. Define indexes that use those analyzers for full-text search, optionally with advanced features like BM25 scoring and highlighting. Cool. Highlighting will be super cool. So advantages of SurrealDB for full-text search. So a unified model, you can keep your data, relationships, and search logic in a single engine. That's actually great. No need to have like separate deployment. Flexible schema. SurrealDB can be schemaless, so adding new fields or text columns doesn't require schema migrations. Powerful query language. So this is like overall sale for the thing. And CPN, welcome. How are you doing? Long time no see. Powerful query language. Yes, SurrealQL blends SQL-like syntax with searching syntax. The add matching operator for full text search queries, advanced indexing feature, etc. Okay, so we just learned the first matching operator. And real-time updates, SurrealDB can handle real-time changes, so newly inserted or updated text becomes searchable quickly. Awesome. CPN is doing good. Awesome. And what on earth is a little crown in the chat? Looks like you just got 50 XP. What the hell's going on? Gives new features in YouTube chat. Top fans. Well, you're fan number 1. Congrats, CPN. Alrighty. Chat leadership thing. Okay. All right. I guess I'm a little bit behind. Huh. Hey, cool. I don't mind it. It's fun. All right. So let's look a little bit more in practice. Creating and migrate and managing full text search in SurrealDB. I expect it to be really simple. Below is an example of how you might define a table for articles. Let me actually zoom it in a little bit because I think it's a bit too small for the stream. Oh, now it's too large. Yeah, this will be good. Below is an example of how you might define a table for articles. Define an analyzer that lowercases and removes accents, and create a full text index on the title and body fields. Okay, so we just switch to the namespace. That's all great. We create a table articles. We mark it as schemaless, so we don't deal with the strict schema. Define a custom analyzer. Okay, so we literally define analyzer, my custom analyzer. Tokenizers class. I guess that's the type of a tokenizer. One of them is class. And filters, we have lowercase and ASCII. So I guess basically, oh, I see. So basically the way I understand it so far is that whatever we put into this table now, there's extra field type attached to it where it will basically process every entry with the specific tokenizer to split it into tokens, filter, convert everything to lowercase, so when comparing things we ignore case, so it's case insensitive, and we remove all non-ASCII characters, like all the accents and everything. Okay, all right. And I wonder if it removes like commas and other symbols. Interesting. So then create a full text search index. So this just tokenizes. Well, this will be additionally create the place for data where actual analyzer's output will be stored. So define index ML title on this table article, right? Oh, so this isn't even attached to a table at all. It just exists somewhere. Like, oh, we have an analyzer. It just exists and we can reuse it across different tables. Okay. So we create this index on a table for the field title. Okay, so this is for a specific field. Interesting. And search analyzer is my analyzer, so we're going to use this one. And we add features like highlights and BM25. And then we create another index, ML body, where it will be on the field body, and basically pretty much everything the same. So that means that other fields that might be passed into this table are just ignored. Okay. And CPN says about the new chat leadership thing, I found it annoying, to be honest. It showed me the benefit of just sitting down and reading the docs. So thanks for that. Oh. I'm glad. That's something that's way easier to do on a stream. Because off stream, for me at least, is way too easy to just try to do the thing. Or, rush it. Here I actually read every word, not just skim it, so yeah, it helps me. Alrighty. So with this setup, my custom analyzer splits text by Unicode class changes. Unicode class changes. Okay, letters, digits, punctuation. And then lower cases and removes accents, turning the string, look, full text search, for example, into the final tokens. Look, exclamation mark is a separate token. Full dash text dash search. So it's all lower cases, and that's it. SurrealDB uses these and spaces, of course, are removed. SurrealDB uses these tokens from the analyzer to build an inverted index over both the title and body fields. The BM25 scoring function is used to rank documents. And highlights are enabled, which allows SurrealDB to highlight matched terms in queries. Okay. So now how to query it? Assume you want to search for articles about machine learning. SurrealDB syntax might look like: select everything, and then we have this fun thing, search highlight. Store, 1. Huh? As body. So we'll have body. This will be what? Some hashtags, empty and 0 as title. I guess this is maybe like for how to rank it. Oh, and these will be wrappers. Yes. So, so the the title that we have will be highlighted by just prepending it with a double hash, so it's like in Markdown, while the body will be wrapped in double asterisks, so that it's like bold in Markdown. I see. And then search score of the argument 0 and search score of the argument 1, they're just added up, so they're equally important as score. Okay, so from article. So we basically select the body, title, and score. Okay, body will be just wrapped in stuff. At least only the part of the body that we actually matched. Okay. And only the part of the title that we matched. Okay, I see. And then we have the score. From article, where the title, we have the double at, and we put 0 as this is our argument 0, argument 1. I guess we number them. So we search in the title for machine, while the body we search for machine learning. Interesting. And order by score. Look at that. Limit 10. So explanation. Search highlight. SurrealDB can highlight the matched terms in text. So I guess we can use that feature because our indexes have it enabled. Search score works with the BM25 ranking function to return the relevant score for the matched document. And then we have the at machine learning. SurrealDB will check if the tokens machine and learning appear in the title field's FTS index. The number in between the two characters of the operator lets the database know in the above functions which part of the query to highlight and calculate a score for. If no search functions are used, this operator will be used as at without a number. For example, if we were just searching for one thing, right? Yeah. Okay. And that's it. Resources. Full text search reference guide, including comparison of full text search to other methods. Okay, so we will open that in a second. We have define index, define analyzer. I'm gonna open them in the background. And search functions, we have highlights and the matching keywords for the predicate reference number. Offsets returns the position of the matching keyword for the predicate reference number. Okay. Search score helps with scoring, ranking. And search analyze used to test the output of a defined search analyzer. Oh, interesting. Okay, so maybe we could try some of that, like in practice. Put a few things in there and see what happens. Let me open up the Surrealist and clear all that. Let me just figure it out. Sandbox. There we go. So I just opened up the sandbox. All right. So do we have anything here? Nothing. It's all empty, right? So we're just in a sandbox. We don't worry about databases nor namespaces. So we're just gonna do define table, right? Let's do our, what are we going to store in there? Something that we can easily create content for. Define table. Let's do articles, okay? Okay. So that should work, right? Okay, we've got our table articles. And it's schemaless, so we don't have to worry about things. So now what we need to do is basically, where was the full example? So we can define analyzer. Let's just go with the same one as here, okay? Let's just go as close as we can. So this will be whatever, simple analyzer. That's how we're gonna call it. Run query. Let's see where it's at, because we have articles and here we have designer. But how do we see all the analyzers and stuff defined? I guess we don't. It just, we don't have a preview specifically for that. Sure. I guess we can live with that. I'm sure there's a way to query that. So next will be basically, defining the indexes, right? So what we're gonna do, we're gonna define two indexes, title and body, okay? We're gonna do it exactly the same. It's just instead of my analyzer, it'll be simple analyzer. ML title, ML body. And so this will be looking for those fields. I wonder if we can actually combine multiple. That's another question. Or how do you define an index, like, over multiple fields? I mean, I believe you can do that. Or like if there's one that just gathers all the fields together. Because let's say I want to allow others to, to build some kind of API where people can send in whatever data they want, and it will be all searchable through that. They can send in whatever fields they want. How do I gather them into like one generic index that can be searched for? Another thing is, how long should the body be? Are there like reasons to start splitting it or something? I don't know. So let's run the query. We should have those two indexes done, right? So in the designer, we can go, oops, I did articles. Why? Oh, because I did find field article. Define table. Yeah, article, singular. Schemas, right? So we're gonna run this. Already exists. Okay, so I guess everything is done for us, right? Article, a single one. Normal table, and for schema is false. We have no fields defined because we don't care, but we have body and title, those indexes, right? So when we click on them, we can see the full thing. Search analyzer, simple analyzer is beat. BM25, and it looks like it takes some extra arguments. I guess we could tune it for something. Doc IDs order, 100 doc lengths order, hosting. So there's tons of extra stuff that we could potentially go deeper, you know. Okay, lengths cache, terms cache. Interesting. So yeah, this is, you can go simple like we did, or you can go deep and actually optimize. Okay, good to know. So that's that. Let's just get rid of this random articles thing. There we go. So we have our article. So now we want to put in some data in there. Okay, so what we're gonna do is we're just gonna copy paste some docs from the from SurrealDB, I guess. So we can probably just do this and start doing stuff, right? So we create article set, and we're gonna do title is, we're just gonna paste in that. Okay, there we go. And body is, we're just gonna put some stuff here, like copy paste and scroll down, right? Although we'll probably have a problem. Can we do backtick? We can, but it still doesn't work. Okay, let's do it simple. This should work up to here. Yeah. There we go. It's all blue now. Great. So this will be our body, and we do that. Let's see if it works. Bam. Okay. Body is empty. Uh-oh. Yep, body is empty. So let's remove this one. What is going on? I guess QL. How do you deal with strings that are, do we need to escape them or something? I don't want to escape stuff. Okay, now it's green, so maybe this will work. Run, body, and title. Okay, so that's good. So I wonder if it shows anything in the Explorer about the article when we refresh it. So we have the body, we have the ID, title, and nothing about the actual index stuff, right? I don't think we can just preview the contents of the index because that's probably a little bit less human readable. But let's just go and, I don't know, let's grab this thing, SurrealQL, that will be another article, and let's just copy some text. This should be good enough. And I'm just gonna run for a few articles and it will be able to start querying. Okay, that's great. We've got second one. We're gonna go over those 3 extra ones. So let's call this one full text search, and we're gonna go up to here. And sure, maybe a little bit here as well. There we go. Whatever. So that's that one. Bam. And we have 2 more. Define index statement. So yeah, this is the repetitive part, but hey, I don't have any fun content to add. And maybe something here. I wonder if I can paste that. Yes, I can. There we go. We have the last one now. Define analyzer statement. Okay, and we're just gonna do. Okay, these already have like quotes in them, so we're gonna go only to here. Still don't know what to search for, but okay. This should be it. Run it. And we should have several little articles, right? We have 5 articles. So now we can start querying. I'm just going to do a new query and let's see. So they said that we could basically query it in this fun fashion. So search highlight, we'll see this stuff and we'll go through article and let's search for machine learning if we have any hits. Limit 10, run, nothing. What if we do search? We should have plenty of results for this. There we go. So first one that showed up is, let's actually remove the body from here because it's a little bit too much. Huh? Still shows the body. Oh no. Okay, I guess this just makes it like overrides the thing. Sure. So we can see SurrealDB offers this and we have the search highlighted here. Another search highlighted here. Okay, there we go. And probably somewhere else is another search. But we can see that the score is negative 0.35. Okay. Well, this one has even more negative and even more negative. Okay. So that's fun. What if I do searches? Nothing. Ah. So what else could we search for? Maybe analyzer. Okay. And we do that, and we have first spot is the article define analyzer statement. Okay. The second result is the using SurrealDB as full text search. Okay, and nothing else contains stuff. So this one has score 0.44. Well, this one has, wow, strong one. I guess this shows that this is strongly about this stuff. And rest is just cut off, like completely, nope, nothing else contains that. Okay, I mean, this is that simple, isn't it? Just, okay, run that and we're done. For what it is, it's awesome. So let's do search analyzer in the body. We'll run this now. Okay, we found the stuff and now the score decreased here. We have this result, a little bit worse score, but still found those two. Okay. So yeah, I can see that working. And basically, without this, we would get still our body and stuff, just not highlighted, right? Still 1 and 2 results, and that's it. Okay. I see. Yeah, this is awesome. This is really simple. So let's read a little bit more about this full text search reference guide. So this is definitely longer and will go way more in depth. Okay. I think we're ready to move a little bit forward, right? We'll go a little bit deeper. So SurrealDB offers a large variety. Let me just make it like full screen. SurrealDB offers a large variety of ways to work with text, from simple operators to fuzzy searching, customized ordering, full text search, and more. In this guide, we will cover comparing and sorting text, contains functions and operators, equality and fuzzy equality, regex matching, string functions, and full text search. Awesome. So what we care about is full text search, but it's also nice to see that we have the fuzzy equality already built in. So we could have, different levels of search. We'll probably combine results in some way. Interesting. Because with fuzzy equality, we can basically accommodate for typos. So I wonder, what if instead of just, we were doing search, right? So what if we have a typo without R? Search. Because just somebody had a typo. And suddenly we have no results, so no fuzzy search in here. Huh. So it would be nice to know how to still get results even though we have a typo in a search, because half the time you search something on Google, you have a typo and it just fixes it for you. So I want the same result. Okay. So this will give you a comprehensive overview of the different ways to work with text in SurrealDB and which one to use in your specific use case. And CPN says try Seach without the R, right? Without extra letters. Still nothing. Yep. So this doesn't do anything fuzzy. Okay, so comparing and sorting text. In select queries, the following example shows a few records created from an array of strings in an order that is sorted to the human eye, lowest to highest numbers, then A to Z. Okay, so we have basically, we create those 1 to 11, Bucko, Kitty, and Zoo. So from the perspective of SurrealDB, this will be first, this will be second, this will be third, fourth, fifth, and probably this being with accent will be the last one. So inside select query, an order by clause can be used to order the output by one or more field names for the above. So yeah, I want to see that. New query. Bam. So we're gonna create some data entries, don't care, and we're gonna sort them. 1, 11, 2, zoo, and then kitty. So first we have uppercase letters, then we have lowercase letters, and then we have the other characters. Okay. All right, I was nearly there. Okay. However, in the case of strings, sorting is done by Unicode rank, which often leads to output that seems out of order to the human eye. The output of the above query shows the following. Yep, I guess we didn't need to run it. This is because 11 is ordered before 2 because the first character in the string 2 is greater than the first character in the string 1. Yep. Zoo is ordered before kitty because the first character in a string zoo is Z, and number 59 in the list of Unicode characters. Lowercase k is 76. Yeah, the lowercase letters come after uppercase letters. Yeah, while the A with the whatever that call that asterisk, little something, register as the Latin capital letter A with acute. Okay, so the little thing is called acute, is way further up the list. So to sort strings in a more natural manner to the human eye, the keywords numeric and collate, or both, can be used. Numeric will instruct strings that parse into numbers to be treated as such. So if we do order by and we just throw in numeric, suddenly numbers are done correctly, but the rest is the way it was. Okay, so it's good to know that it will just correct those. Collate instructs the Unicode strings to sort by alphabetic order rather than Unicode order. So if we're going to do that, without a numeric, the numbers are still screwed up, but these are fine. Okay. And for the data in this example, collate numeric is like what we wanted. Exactly, this is how your computer will sort, I don't know, your folder names, right? And file names in Explorer, if you sort by name. Okay, so then we have sorting functions. So, I mean, this is very useful, especially when we start going to this kind of stuff, right? Sorting functions, as of now that I think about it, this is actually fun to do on a database side if it's just throwing in two characters, right? I mean, two little words, and you have this result, and you don't need to do any sorting on your application end. That's actually awesome. So sorting functions. As of SurrealDB 2.2.2, the functions array sort natural and array sort lexical and array sort lexical natural can be used on ad hoc data to return the same output as the collate and numeric clauses in a select statement. Okay, because this whole thing is like, we have this whole select value, this and that and that. But if you're dealing with some array of stuff that already exists somewhere, maybe from other select statement or something else you extracted it from somewhere, maybe your val had a field that's a list of stuff, right? Then you can just use those to wrap it and get a new array. Okay, very nice. So that's so much for sorting. Let's move on to contains functions and operators. Okay, so this is not specifically text search, but related, right? The most basic way to see if one string is contained inside another is to use the in operator or the string contains function. Okay, so we can say ample in Rumpelstiltskin, whatever that is. So I guess this will be false because we have uppercase U, right? We're comparing exact data, so this doesn't match already, the uppercase. String contains, we have the same case. And same function using method syntax. Of course, you can just do nowadays, this is my string dot contains ample, right? I love that you can do it all three ways in a language. It's fun. While if we do it to lowercase, they all will switch to true. Okay, so that's great. That's simple, and it's good to know that we can just check for inside of a string, right? So that's fun. SurrealDB has a number of operators so to determine if all or some of the values of one array are contained in another. Okay, so we're switching to something else, such as contains all and contains any or all inside or any inside. I guess so contains all and all inside is basically the equivalent, right? The operators with contains and inside perform the same behavior just in the opposite order. Ah, okay. So yeah. 1 to 3 contains all, 1 and 2. And it will be true because 1 to 3 contains both 1 and 2. While 1 and 2 are all inside of 1 to 3. Okay, just different order. Great. Because strings are essentially arrays of characters, these operators work with strings as well. Oh. Oh, so we could basically say, let's say that we have my name, right? Benjamin. And contains all from Ben. This should be true. Oh, it's false. Oh no. Um. Oh. B E N. How about that? False. Oh. I guess it doesn't. Because strings are essential arrays of characters, these operators work with strings as well. No, they don't. At least not for me. So, oh well. That's something worth investigating, I guess. I'm gonna write it down. It would be nice to have that example here because maybe I'm just doing something wrong. Oh, there is. Oh, okay. Thank you, CPN. I kind of stopped here. It looked like okay, this is the end of the section. Silly me. Both of these queries will return true. Example, this contains all ample and kin. So I would need to this contains all and one of the this thing, right? This should work. doesn't. Contains all. This doesn't work. So SurrealDB version 2, 2, and 2. What is the sandbox running? Oh, look at that. Sandbox is running 220. Oh no. What? This is the most up-to-date surrealist. Hey, at least they weren't wrong about that. Let's fire up Docker, and I think let me just quickly update stuff on there. Not this. Please go to container. Just doing some stuff off screen, so just bear with me. Homelander. And will it start up or not? Okay, start it up. We have the very old Postgres Surreal benchmark. Whew. I guess we can use some of that. No, 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 no. SurrealDB. What is the current version of SurrealDB? Let's create a new tab. SurrealDB Docker Hub. And let's see. Current image is 237. Okay, so let's go with the 237. Version 237. This is good enough. Good enough. What the heck? Okay. I'm just gonna start up some random stuff. All right. Gonna go all default. You go away, you go away. And we're gonna have a thing running in a second. Now let me just check for the variables here. And we're going to the Docker Surreal bench at that point. Let's just create a new folder. It will be Surreal Learning. Okay. And I guess I'll be able to just run it. Update. Okay, this seems to be running. So let's try to connect to it so that we have a fresh thing. We had something like this, right? This is supposed to be Surreal 2. This is old stuff. 14841, and this is not Java, this is Homelander. This should be all the same. Surreal Learning. Save changes. Will we connect or will we not? This looks like it's running. Everything was created. Localhost. How about that? Oh, now it's working. There we go. We're good. And we were running some examples. Element contains all. Then. True. There we go. Now it's working. Okay. Okay. So we're just running on a most up-to-date thing. Good. Okay. We can close this and get back here. Okay. So we can just straight up do all the variations. So that's fun. That's good to know. Then we can check if the sentence has all the keywords required or something. Fun. Okay. So equality and fuzzy equality. While strings can be compared for strict equality in the same way as with other values, fuzzy searching can also be used to return true if two strings are approximately equal. The fuzzy operators are just tilde to check if two strings have fuzzy equality, not tilde to check if two strings do not have fuzzy equality. Oh, okay. And this one to check if any strings have fuzzy equality. Oh, any string. Okay. I guess we put arrays. Yeah. And to check if all strings have fuzzy equality. Oh, interesting. So this should be fuzzy to this, right? They all return true. Okay. So that's simple. This should be true because they're very different. Big, small. So any of them need to be fuzzy to this one. Okay, and all of those need to be fuzzy to this one. Okay, I can see. I see. This is easy, but to what extent do we define similar? Right, because this uses fuzzy matching is based on the Smith-Waterman algorithm that requires some time to understand. It is a convenient option due to the tilde operator, but can sometimes produce surprising results. Like United Kingdom to United Kingdom. It's true, right? But United Kingdom, similar to IDIT. True, second string entirely contained in the first. Oh, huh. Okay. I guess it compares the right one to the left one. Okay. And this one's fine too, because just, yeah, okay. While when we put a different character, so when we have an actual typo, it won't work. Interesting. Why is that? Just we have one O with what was it called? I already forgot the name. There was a something for that little line. The string similarity fuzzy function can be useful in this case, as it returns a number showing the similarity between strings, not just whether they count as fuzzy match. In the following example, while the strings IDIT and I do have a similarity score above 0, they're ranked much lower than the better matches. But what about the... Okay, so let's just do this manually, okay? Because I want to kind of get it. So United Kingdom, so that's our thing on the left, right? So if we're gonna do just perfect, right? This should be absolutely perfect. We get 295. If we add a few things, will the score increase? Yes. I guess the more characters, the more points, because we matched more characters. Okay. So what if we just do, so this is 295. If we're gonna add another one, which will be lowercase k, right? Um, why do we get one result? Not individual. I want table. Nope. Combined. Okay, there we go. Okay, so the score decreased very little. If we're gonna do both with something like that, score again, so lowercase to uppercase is very little. But what if we're gonna do the same thing, but instead of kingdom, we do lingdom? Whoa, no match at all. So this won't match to a typo. Okay. Just straight up won't match to a typo. While something like United will match just with lower score because only the United word matched. Okay, usable, but too bad we don't have, you know, we don't allow for typos. Huh. Yep, they showed this thing. Other similarity and distance functions. Okay, so we have more of them. SurrealDB offers quite a few other algorithms inside string functions module for distance or similarity comparison. They are, we have Damaro-Levenstein, normalized Damaro-Levenstein, Hamming-Levenstein, normalized Levenstein, OSA distance, Jaro and Jaro-Winkler. Whew. Which of these functions to choose depends on your personal use case. For example, fuzzy similarity and distance scores are not a measure of absolute equality, and ordered similarity scores could only be used in comparison against the same string. Take the following queries, for example, which return a score for the string united and unite. Return 131 and 111, also returns 131 and 11. Yeah, exactly. Because whatever matched the score is based on, it doesn't care if, what the line was here. Okay, I see. I'm just kind of running quickly through that now because this is lots of stuff that I'm not super interested right now because I want full text search, but it's good to know. So while the word unite is clearly closer to the word united than it is to United Kingdom, the algorithm used for this function only considers how much of the second string is found in the first string. However, the string similarly Jaro function returns an output that approaches 1 if two strings are equal, making it a more apt solution when the first and second string may be entirely different. Ooh, just Jaro, right? So let's see what this looks like if we're gonna replace with Jaro. So first one was perfect. Second one is 0.95 because of just this. Oh, look at that. This one is also matched. The same as this one, even though this one is K but lowercase, while this one is completely different character, although it's next to the keyboard. What if we're gonna replace it with something that's at the other end of keyboard? Doesn't matter, it's just one character is wrong. Okay. And then we have just united without entire kingdom, which again decreases the score. Okay, so Jaro is nice, and we had Jaro Winkler. The hell? Winkler. Okay, a little bit different score. Depends on something. Okay, that's fun. Good to know. Another example of large difference between algorithms is the Hamming distance algorithm, which only compares strings of equal length. Oh, only for equal length. Okay, I guess because of that, it has some other advantages. Okay. So then we have regex matching. Oh dear, string matches function can be used to perform regex matching on a string. Guess one needs to be really careful with that. It probably can get very costly very quickly. And then we have other string functions. SurrealDB has a large number of string functions that can be used manually to refine string searching, such as lowercase, starts with, or ends with. Yep, nothing crazy here. For more customized text searching, full text search can be used. And there we go, finally, full text search. Full text search supports text matching, proximity searches, result ranking, and keyword highlighting, making it a much more comprehensive solution when precise text searching is required. It's also ACID compliant, which ensures data integrity and reliability. So we have a little bit more about defining the analyzer, right? The first step to using full text search is to define an analyzer using a define analyzer statement. An analyzer is not defined on a table, but a set of tokenizers to break up text and filters to modify text. Okay, yep, it's just globally available for the database, I presume. I wouldn't expect it to go outside of the database. The define analyzer page contains detailed explanation of each type of tokenizer and analyzer to choose from. To define the analyzer that most suits your needs, it's recommended to use the search analyze function, which returns the output of an analyzer for an input string. Exactly. So we will later look into different types of those tokenizers and other parts, because this is like crucial in how your full text search will actually work. So take the following analyzer for example, which uses blank to split a string by white space, and edge ngram 310 to output all the instances of the first 3 to 10 letters of a word. To output all of the instances of the first 3 to 10 letters of the word. Oh, okay. Interesting. So define analyzer blank ngram. Tokenizer is blank, so it will split into words, and edge ngram is just a filter. So search analyze blank, yeah, this one, and we just put it in here, right? The output includes, oh, so search analyze just shows us what this thing will turn into, right? So the output includes strings like turns and legend, which include punctuation marks. The wheel. Oh, look at that. So it adds more like variants to search for. Wheel, Tim time, turn, all those fun things, right? But legend, for example, here has the period at the end because we use the blank, right? The blank tokenizer that just splits by white space and nothing else. If this is not desired, some looking through the define analyzer page will turn up another tokenizer called punct that can be included, now creating an analyzer that splits on white space as well as punctuation. Oh, so we can put more than one tokenizer. I guess it then found the legend and turned it a dot, right? But no, we just don't have a dot at all. Oh, because this probably makes it ignore stuff completely. So let's try this. I want to see. So we're going to define this thing, right? We're going to run it. Oh, a namespace to use. Oh, right. Create namespace test 1. Well, let's do stream 13. Okay, there we go. And we create database. One, whatever, doesn't matter. Okay, run query. So we see all those here, right? But what if I'm gonna do ngram from 1 to, let's say, 3, to just remove the number of stuff and rerun it? Already exists. Great. Can we like override it? Find analyzer, override. There we go. We can do that. So we were going in here. Define analyzer, override. There we go. Run. TTHE, where of times. So we should get that period. Oh, there we go. There we have a comma and we have a period. So they are still included. It's just, I guess, first the blank tokenizer split everything into words, and then the punctuation went over each of the words and found the turns and split that into 2 extra words, and then it found this one split into two separate sections and also this one. Okay, so we can just do both. Okay, all right. And how would class work? Because we used that at some point. Run. The wheel of time turns, comma. We got the same result. So we're gonna need to learn what's the difference between class and blank and punctuation. Maybe it's literally just those two combined. So tokenizers and filters. The available tokenizers and filters are as follows: blank, camel, punct. So split by white space, camel case, and punctuation. The class tokenizer splits when a class change is detected, such as letter to number, space to letter, punctuated letter, and so on. Oh, okay. So that this would basically make it if we have something like wheel 1 to 3, or let's do W12, okay? With this thing, W12 will be an actual one word. We're gonna switch it to class. It will split it to W and separate 12. Okay. I see. And filters, ASCII, lowercase, uppercase to change to ASCII, lowercase, and uppercase. The n-gram filter is similar to the edge n-gram filter above in that it takes a minimum and maximum length, but instead moves from character to character inside a string as it attempts to find all possible outputs in between the two lengths. Oh, geez. That's a little bit more. Because the word cars was just crazy. Okay. So the snowball and mapper filters are the most complex and versatile. The snowball filter The snowball filter is used to perform stemming, the reduction of a word to a basic and universal to as basic and universal a form as possible. It is available for the languages Arabic, Danish, Dutch, English, Finnish, French, German, Greek, Hungarian, Italian, Norwegian, Portuguese, Romanian, Okay, not all the languages, but bunch of them. Okay. Stemming involves using an algorithm to reduce a word, but is unable to incorporate complex changes like the plural and verbal vowel changes in English. So snowball test, right? We have the analyzer just splits the words and stuff, and snowball English. So we give it manager. Oh, we give it basically this text, right? Manager, managing, and management. So all that turns into manage. Okay, all those three. Running and run will be run and ran. Okay. And we have foot, feet as, because these are different plurals, right? Introspect. Yep. Okay. And now we've got stemming is particularly useful in languages with complex but regular declension. What on earth is declension? Stemming is particularly useful in languages with complex but regular declension, such as Finnish. In the following example, the snowball filter is able to turn all declined forms of the word talo, house, into its root form. Okay. So we have declension. Okay. I understand the word now. So talo, talon, taloa, talosa, all those versions of the word that exist for different, cases and whatnot, right? But they're all talo. Okay. They all actually begin with talo, but yeah, that's great. Awesome. And then the mapper filter. And CPM says this is cool. I guess this was regarding some of those tokenizers. Yeah, that's pretty interesting how it splits it, yeah. And how that works. Never really went into learning about full text search and stuff, so this is fascinating. So there's lots of math behind the scenes and algorithms that probably try to be as efficient as possible while dealing with complex tasks. Okay, the mapper filter. The mapper filter is the most customizable of all, involving a list of strings, and the strings, they are to be mapped 2. Oh, this filter requires a path to a text file inside which each base form is followed by a word to, to map to it, separated by comma. How am I mapping to a file when I'm running in the database? What? Run, foot, feet, right? So, okay, so we'll take the word run and ran. So I guess these are equivalent, and foot and feet, they're equivalent, right? In the case of above example, the mapper will allow the output to show the base forms of the words run and feet. So we have define analyzer, mapper, tokenizers, blank, filter, snowball. And after the snowball, when it reduces everything to those stems, then we can apply the mapper to kind of reduce it further. And therefore, running run will be run. Foot and feet will be foot. Okay, great. The word mapper was intentionally chosen to be ambiguous. This is as this feature can be used to map any string to another string. Could be used, for example, to map cities to provinces, planets to stars, hieroglyphs to English words, and so on. Okay, seated man is this. Man with a hand to mouth is this, right? And we just do this analyzer, we run it, and we give this, so it's going to replace it with stuff. So that's how you could, for example, deal with emojis, I guess, so that if you put emojis, so this is pretty much it. Yeah. You can make it where in your text, your analyzer will basically replace all the emojis with like their text equivalents. So when you're searching through stuff, you're actually getting some good stuff. Okay. What the hell is this? Never mind. Okay, great. So defining a full text index. Once a search analyzer is defined, it can be applied to the fields of a table to make them searchable by defining an index that uses the search analyzer clause. Having a full text index in place makes it possible to use the add operator, the matches operator. Okay. So yeah, we go on and we have nearly the same examples before, right? And where we had the tokenizer class, lowercase and ASCII. And we define the index, body index for the field body, bam, and the same one for title. So we went through that already. And here we just create some 2 articles, right? Machine learning, history of machines. And we search for the machine in body or title, and it should find both of them. Yep. Okay. Found them. To use highlighting and best match scoring on searches, the BM25 and highlights clauses can be added to the define index statement. These enable you to use the search highlight and search score functions. Inside a query, the the matches operator takes a number that is matched within the same number passed to these functions. In the example below, where text we have 0, night, part of the query will match with search highlight, and it will be wrapped in arrows, 0. And search score, 0 as text score. Okay. Well, 1 will match to just 1. Okay, we've got those 2. We have our articles. And here we have an example of 0, 0 matches to this one, while 1 matches only to this one. Okay. So this is nothing new. Oh, wow, we learned nothing new. Great. But we learned something about tokenizers and filters, so I guess we can go deeper, right? So let's just have a quick look at the analyzer statement to, to finish that topic and move on to the actual indexes, because I think the combination of both gives the best results. Okay. So the finalizer statement. In the context of a database, analyzer plays a crucial role in text processing and searching. It is defined by its name, a set of tokenizers, and a collection of filters. The output of an analyzer can be experimented with by using the search analyze function. That's awesome. And requirements, you must be authenticated, yeah, and you must be in your namespace, yes. And database. Okay, so this is each analyzer is defined per database. Okay. So that's great. Statement syntax, so we'll have define analyzer, potentially override, or if not exists, its name. Optionally a function. That's interesting. Tokenizers and filters, and of course a comment. So the function clause. Using the function clause allows a user-defined function to be executed on the initial input. The function must take and return a string. Oh, that's fun. So we could kind of remove some things out of it, right? Or like in this example, it just puts a sentence backwards or something. Oh, each word is basically backwards. Yep. What the hell? Split by characters fold. Oh dear God. Yeah, I'm not gonna think about that, but yeah, okay, so we can do that. So I can already see that, let's say our text will deal with, let's say, removing some maybe maybe your titles have some kind of typical, like in parentheses, some extra segments. Maybe your body of something has some special markdown tags or something. Maybe front matter, right? When you're uploading your articles to the database. And this way you could just straight up attach your own function that will first remove, let's say, all the front matter and, I know, emails out of the text, so that, you know, when it's being turned into tokens, it's just, you know, it doesn't contain any of those emails or other things that you wouldn't want. Or maybe add something, who knows. But yeah, that's fun. And tokenizers are responsible for breaking down a given text into individual tokens based on a set. Wait a moment, does it mean that if I can run a function here, does it mean that my function can perform other database things like increase a counter or do something? Oh, this is fun. I want this as an example. Oh no, my brain goes into that weird thing again. So let's just rename it not backwards, but maybe log string, right? We take input, and instead of doing stuff here, what we're gonna do is create log message set text is input. Okay, and then we do return, or we probably just do input. Okay, return it, and we define this whatever logging analyzer. Okay, and we run this. Couldn't write to a read-only transaction. Oh, so we can't do that. All right, so basically an analyzer is something called read-only transaction. So that's something new. So we can't do fancy stuff like this. Okay, but I wonder what other things are considered read-only. Can we put an HTTP request here so that something happens? I don't know. And an interesting idea. What is actually allowed to put in there? I mean, most of it wouldn't make sense because you want usually those things to be performant, but you know, why not? So too bad. Too bad. Okay. So tokenizers. Tokenizers are responsible for breaking down a given text into individual tokens based on a set of instructions. There are a couple of tokenizers that can be used while defining an analyzer as seen below. So I've got the blank one. We saw it plenty of times, so it should be obvious. Um, okay, okay, and it just splits into words based on white space. Breaks down text into tokens by creating a new token each time it encounters a space, tab, or new line characters. Okay, space, tab, or new line characters. So basically white space, right? It's a straightforward way to split text into words or chunks based on white space. Now we've got camel. The camel tokenizer is used for identifying and creating tokens when the next character in the text is uppercase. This is particularly useful for processing camel case or Pascal case text, common in programming, to split them into meaningful words. Okay, so that's probably if you want to maybe make your code searchable, right? Maybe you want to make some kind of RAG for searching through code. That could be something. All right. Then we've got class. The class tokenizer segments text into tokens by detecting changes, digit, letter, punctuation, blank, in the Unicode class of characters. It creates a new token when the character class changes, distinguishing between digits, letters, punctuation, and blanks. This allows for flexible tokenization based on character types. So yeah, the class is like the base one, definitely, where exclamation mark is separate, 1 to 3 is separate. So all those things are, you know, 4 separate things. So it's not good for tokenizing your passwords, I guess. And then we have punced. The punced tokenizer generates tokens by breaking the text whenever a punctuation character is encountered. It's suitable for tokenizing sentences or breaking text into smaller units based on punctuation marks. And CPN is asking a great question. Can we implement a custom tokenizer? That's a fun question. I wonder if it's possible. I'll check on that. The file analyzer, example, punced, tokenizer, punced, search, analyze, bum. Yeah, and then we're gonna get this thing. So they don't mention it here, but let's see if we can define one. Clauses, define. No, there's no defined tokenizer. Probably not. But if you really, really want SurrealDB as an open source project written in Rust, so you can probably ask your AI agent to just implement it for you, or just set it up and you just implement it yourself. So yeah, and it probably is easy to compile too. Never tried, but that would be fun. Yeah. Okay, so there's not a lot of different tokenizers. We just have few of them. My first thing that I'm thinking about is like, what if your specific case actually needs to like preserve the spaces and tabs and white space? What if we need to actually preserve it and turn it into something important, right? That's what I'm wondering about, because yeah, maybe you need to preserve that, right? Kind of dumb, but maybe your use case would need that. But no, you could probably do a lot of that function to replace it with something else, and then, ooh, yeah. So let's say that our thing here, instead of a log string, let's call it white preserve white space. Okay. So, oh, that means I need to find all the instances of spaces and stuff. Yeah, this will need to have a code that basically, whenever it finds one space, replaces it with something, right? All those fun things. So in theory, huh. Let me see if we can actually go and find something here. Functions, database functions. Do we have something like this map? Oh dear. That's a bad search. We have arrays. but I want in text. So let's go with string functions. Do we have something like this whole mapping thing? Repeat, replace, reverse. I mean, we can do replace. That's one thing. Um, Trim distances, HTML is, and that's it. So I guess we could just do replace, bunch of replace for fun. String replace, string, string, string. Um, um, After 2.3. String, string, erratic, regex of string. This is text. So I guess that's the text. What we're replacing with what? Okay, so we could, in theory, do something really, really dumb, and let's say let whatever v1 is replace the input, where we take all the spaces and replace them with something like um um uh some random space or whatever space character. Okay, so we just replaced all the spaces. Then we're gonna do where let v2 is, what am I doing? V1, and let's say, I guess this will be tab character. And we're gonna do one more for new line, and that should be it. And we return the v3. So that should replace a bunch of them. So when we suddenly, I like SurrealDB, new line, this is more text, and we'll just throw in tab in here. What's going to happen now? Define function, preserve, yeah, sure. Override. Sorry, overwrite. I'm gonna do the same here. So in theory, yeah, it's space character like, oh geez, this turned it into a single word. Okay. We just add spaces around it, and that's gonna work. There we go. There we go. And then we could potentially go with the filter mapping that will replace it all into something. So yeah, you can do weird stuff, I guess. So let's get back to our define analyzer, and we're gonna finish it off with after we learn the filters, right? So filters take on the task of transforming these tokens for further processing and analysis. The ASCII filter is responsible for processing tokens by replacing or removing diacritical marks, accents, and special characters from the text. It helps standardize text by converting accented characters to their basic ASCII equivalents, making it more suitable for various text analysis tasks. Okay, so this basically example ASCII and resume cafe. So we'll do resume and cafe. We don't have all those special characters. Does it work with Polish language? Let's see. I want a new query. Where did my query thingy go? This? There we go. Ah, I can fold it. That's fun. Never knew that. So let's do uh um what are the other characters? Now all. There you go. A few Polish characters, right? And let's also do the big versions of it, right? And let's see if what's gonna be a result of this. Ah, look at that. It removed them, no problem. Okay. So compatible with Polish language. Great. Um, sure. So lowercase, the lowercase filter converts tokens to lowercase, ensuring that text is constantly in lowercase format. This is often used to make the text case insensitive for search and analysis purposes. So I could the ASCII comma lowercase, right? Uh, lowercase. Right? How do you add multiple? Do I put commas in there? Lowercase comma, yeah. So we're gonna do, yeah, I guess it's gonna work. Let's just do override. Right, actually. And there we go. And in this case, I could, in theory, first go to lowercase and then ASCII. And it works as well. Doesn't matter. Okay, great. And CPN is referring to my implementation and does that is a solution but a lot of work. Yes, it is. Okay, so uppercase, the same thing. The uppercase filter converts tokens to uppercase, ensuring, yep, case sensitivity. For example, if you had the hello world, it would take it to hello world. And that's basically the same thing. And then we have this funny edge engram. The edge engram filter is used to create tokens that represent prefixes of terms. It generates a sequence of tokens that gradually build up a term, which can be used for autocomplete or searching based on the partial words. Oh, autocomplete is a good idea here. It accepts two parameters, min and max, which define the minimum and maximum amount of characters in the prefix. So apple, banana will be app, and B-A-B-N. Okay. Okay. So from 1 to 3 characters. Okay. And then we've got the mapper. There we go. The mapping filter is designed to enable lemmatization within SurrealDB. Lemmatization is the process of reducing words to their base or dictionary form. The mapper mechanism allows users to specify a custom dictionary file that maps terms to their base forms. This dictionary file is then used by SurrealDB's analyzer to standardize terms as they are indexed, improving search consistency. This is particularly useful for handling irregular verbs and other terms that the default snowball filter cannot handle. Lemmatization files are easy to put together and to find online, making it possible to customize full-text search for smaller languages. Look at that. I like that. How does the mapper work? Configuration. In the SQL statement below, the mapper parameter is specified within the analyzer definition. This parameter points to the file that contains the term mappings for lemmatization. Okay, so define analyzer, lem English, organizer, blanket class. Why this and that? Why not just class? Class already skips all the blanks. Huh? That's confusing. And filters lowercase, and then we've got mapper, and we point to some file that magically exists somewhere on a server. I guess if you install it on your own machine, that's fine. And with Docker, you would need to probably just map that file, and that's it. So return, search, analyze, lem English, he drove, and swum. Okay. Yeah, he drive and swim. Dictionary file structure. The file specified in the mapper parameter must follow this format. Each line contains a pair of terms separated by a tab. The first term represents the canonical base form of the word. Second term term is the form to be mapped to this base form. Okay, so it's just a pair on each entry. You can't do like one word and several things that will be replacing it. That will be replaced with it. Okay. So drive driven, drive drives, drive driving, and drive drove. Okay. So too bad you can't do drive, driven, drives, driving, drove, because that would be more fun. But sure, that's good enough. Very simple. It probably file is loaded once, turned into mapping, and then just kept in RAM. Usage. When this analyzer is applied to a text, any word that matches the map term in the dictionary file will be replaced by its base form before indexing. Ooh, what if what if you have one thing that replaces the other thing, and then that other thing will be replaced with another, and can you just apply multiple mapper of the same mapper multiple times? That could be fun. Huh. Okay, great. This helps ensure consistency. Yep. By using this custom dictionary-based mapper, you can control how irregular forms and their variations index, making search behavior more predictable and comprehensive. The following example shows how lemmatization can be used to generate a list of words and their respective frequencies. Oh, other notable functionalities in the example are the string is alpha function inside array filter to remove all non-alphabetic strings. Non-alphabetic strings. Okay. The type thing function to construct the record ID from two strings, and an upsert statement to create a record if one does not exist or update otherwise. So we have define analyzer, lem English. We tokenize by blank and class. Again, I don't understand why one would use two at the same time. Very, very just not sure about it. Now we have lower filters lowercase and mapper into the English lemmatization. So let text is, and we have the little time turns, and we have this long text, right? So we do let words is so you can do it like in normal stuff. So you can use that analyzer not just for indexes, but you can actually, use it within your function or queries to just, hey, give me all the words in that text that user passed, right? Oh, that's fun. All the words there. So we take all the words, then we filter them, right? Where only the alpha numeric characters are returned. So because we did blank and class, mostly the class, that means that we have things like punctuation as separate tokens. We have just numbers as separate tokens, right? All that is separated. Therefore, we can just discard all the non-words things. Okay, so for each word and words, upsert type thing, word, set frequency increased by 1. Oh, I didn't know about this fun feature. So with upsert, when a record doesn't exist yet, the table word and the actual word, when it doesn't exist yet, the frequency will be null, which doesn't exist. So we do plus equals 1. I guess it assumes that it's 0, so it's going to set it to 1. But if it already exists, it will fetch it, read the value of frequency, and increase it by 1. Okay, so basically we have the counter. So that will do it many times over something, but it will just end up analyzing it. Okay, sure. And then select everything from word where frequency is larger than 3. I really want to run it. Oh, but I don't have the lemmatization thing. Okay, but yeah, this is a fun idea. I like it. I do like it. Okay, and result is like frequency of the of age, A, B. Yeah, that's fun. Huh. Okay. A mapper can also be used for ad hoc filtering, as long as the file referenced contains two single words separated by a tab. Take the following file, for example. not found, and found not found, right? But can also be used for ad hoc filtering. Oh, so basically, like, we can take all the found not found, or Datei nicht gefunden, or Fischer not true. It's another language, right? They'll all be just replaced with not found, or all those versions and languages will be in timeout. Okay, so something like logs or whatever from multiple places, different languages could, in theory, just be simplified. An analyzer that uses a single mapper filter can use this lemmatizer to unify multilingual error messages into a single output. Yep. Great. Example using the same mapper to search for errors in multiple languages. Oh yeah, it's because we can just say, this is our error filter, right? We get errors on table uh, index override, errors on table, fields message search analyzer, error filter. Okay, so create error, set message, replace time now. Okay, so this does perform the full text search for the not found, and it will basically find all the, basically all the, what do you call them? All the messages that have the not found in them or something. Okay. Mm-hmm. And then we've got the n-gram in Max. The n-gram filter is used to create sequences of n tokens from a given sample of text or speech. These items can be syllables, letters, words, or base pairs according to the application. It accepts two parameters, min and max, which indicates that you want to create n-grams starting from minimum to size of max. So define analyzer, example n-gram tokenizers class filters n-gram 1 to 3. So if we do apple banana, we have app, pl. Yeah, it goes and generates a bunch of tokens. And I guess this could be used for another fun little things. I'm sure it has important use. Okay. And CPN is asking, are you using SurrealQL in serious projects? Define serious. Recently, I made a little project called MCP board.dev where, it's like an MCP server for your AI agents like Claude Code or maybe Cursor. And it helps you create steps and whatnot. So if I would go to dashboard, let me just log in on the side because I don't know what emails will be showing up here. Yeah, I mean, I don't have any plans here, and this is not a pro account. Oops, I don't have a pro account, so it's like, sorry to unlock pro. But you can create plans with steps and whatnot. So let's get rid of this. Let's go here. Like you can see that, hey, this has multiple steps and it will guide your agent through that. So each step is actually a record on SurrealDB. They're all linked together. They build trees. You can do stuff. So it made it pretty simple to make and expand. So yeah, that's one project, and another project that I will be wanting to use. Yeah, I guess that's a serious project. It will get serious. Right now, it's like very early beta. If you wanted to try it, just go ahead. It's for free. For free, you can basically your AI can submit stuff and do things, and you can monitor the execution UI or request breakdown into substeps of some stuff. They have Pro where you can just do stuff manually and whatnot. So yeah, that's that. I mean, in a dashboard when I get back, in theory, never mind. This is not. The stream is not about that. But yeah, I'm learning about the full text search in SurrealDB because I want to make a little search as a service where, let's say you have I know you made a small e-commerce site where you, I know, sell your artisan coffee, right? And or some other thing. You have maybe just a few hundred little items that are selling, and you don't want to pay $30 a month for some of the big existing searches, especially that you don't have that much traffic. So that would just, eat a lot of your cost. Cost would add up. So I want to make a little thing where for you can start from like $1 a month to have a relatively simple search service. So you just spend 5 minutes integrating into your project, and you have just something working, right? And if you start scaling, of course, the cost will start scaling, but initially it's like, $1 or maybe free. I'll see what happens. And that's why I'm looking at all this stuff now to see if SurrealDB will help me do that. Okay, so where were we? We were in Define Analyzer. It's a snowball language. Okay, so the snowball filter applies snowball stemming to tokens, reducing them to the root form and converts the case to lowercase. The following supported languages can be passed as parameter in snowball: Arabic, Danish, Dutch, English, French, German, Greek, Hungarian, Italian, Norwegian, Portuguese, Romanian, Red. Why am I reading all those languages? So yeah, we learned about that, and it basically turns them into those basic stems. It's just uh, doesn't apply like the mapping of some special words into special words. NCPN says $1 is still too much for that, in my opinion. Uh, I guess that's when I will build it and see how much it involves, because I want to self-host it first. It's like a mini test project. I'll make it open source. Uh, you know, I will host it and see if I can just host it in the home lab for free, and if you get to certain number of searches or something, or how much data you store, then you start getting charged, or maybe you'll be like, it all depends on, let's say, if I will go below $1, it might be will start costing me to charge you that small amount, because Stripe will be like, oh, sorry, minimum thing is this and that. Haven't gone that far yet. I'm just exploring right now. And $1 is still like 21 times less than other cheapest popular solution. Okay. Using if not exists, I can skip that because that's like for everything. The same thing with override. More examples. The examples on application of analyzers to indexes can be found in the documentation of define index. That's where we're going next. This example creates an analyzer that tokenizes text based on the class of characters and then applies the lowercase filter to the tokens. Find analyzer ASCII tokenizers, class filters, lowercase ASCII. Yep. And this for processing English text, yeah, we divide by class and snowball English. For the completion tasks, we do analyzer without a tokenizer. Look at that, no tokenizer. We just generate engrams from 2 to 10 characters. There you go. And this example creates an analyzer specifically designed for source code analysis. Okay, so we divide into words and numbers, then divide by camel case, and then we just lowercase and ASCII everything. Sure. This is easy. NCPN is asking, can the search functionality be added within the backend server? It absolutely can be, but let's say that you just created some kind of a static page where maybe you use Astro or something to generate a nice page. You want to have search option because maybe you have let's say 300 blog posts, right? I don't know. I'm sure there are blogs with that many, or maybe you have some. Yeah, like maybe you made one small website that takes in all the recipes from from online, and maybe you keep adding yours. So you have maybe 2,000 entries, right? But it's your hobby project. You don't earn much on it, maybe some things from ads, so it's just pennies. But you really want this functionality where somebody who's on your website will start searching for other recipes. Maybe they will put in some ingredients or something, right? And suddenly, to make this search happen, it's your static page. You don't even have a backend because it's all static HTML pages with some JavaScript on them. If you wanted to do it on the client, as in a browser, that means that you will need to send all that, include all the data for recipes and everything on each page to do the search, which would be just, it's not viable. Another option is like, oh, now I need to deploy my own backend, and maybe this project isn't worth it. You suddenly don't want to host it somewhere. You don't want to spend another 2 days making a backend just so that you have search functionality. That means that you need to figure out how to send the data to your backend, implement all those texts. So, this suddenly becomes non-trivial piece of work to just add that search. What if during your build process, you could just send all your articles, all your recipes into the search as service so like they get updated or something, right? Just send everything. It gets automatically processed, and then on your front end in a search box, when somebody types in text, hits enter, it just sends one request with the query to the search as engine and gets a list of articles to get, right? And this way, you as a person who creates that, maybe you spend 15 minutes making the upload and the functionality. You just make sure that we have some JavaScript to have a search box and done. And you pay, $1 a month. You don't need to host anything, right? So that's the idea to make. I actually want to call it crude search because it'll be simple functionality, but dirt cheap. You don't have the great big analyzing and metrics and whatnot. But I also want to go into vector search. So for extra, you could actually have LLM search, which could be fun. And, this is my opportunity to learn about full text search and learn about, all the RAG stuff, how to, vectorize or whatever, get the embeddings of stuff and whatnot. I want to go into that. Okay, so we finished with the define analyzer, and now let's go into define index and see if we have something about the full text search, because we have define index statement, and we can see that we have basic stuff on what we do, on what fields, right? We can make it unique, and then we have, besides the actual fields, we have the search analyzer that we can specify. We can optionally give it BM25 with some values or highlights, so there's no other ones. And then we have even more like entry dimensions, whatever that is, and HNSW dimensions. Something tells me whenever we have dimensions, that means this will be vector embeddings. So this will be AI stuff, while this is our full text search stuff. Okay. So next types, we have unique indexes. Yes, I'll just gloss over things because we went through some of the stuff initially. I just want stuff specifically indexes for text search. Non-unique indexes. Okay, we just don't have the unique keyword. Composite index so that it's on multiple fields. And full text search index enables efficient searching through textual data, supporting advanced text matching, features like proximity searches and keyword highlighting. The full text search index helps implement comprehensive search functionalities in applications such as searching through articles, product descriptions, and user-generated content. Okay, let's create a full text search index for a name field on a user table. Okay, so define analyzer. We have the analyzer, nothing crazy, just class and ASCII. Define index, name of the index on table user for the column name, and search analyzer is example ASCII. And we just give it the BM25 for uh, what was it, like relevance score, and highlights to be able to highlight where the search was found. Okay, and then we got search by using the search keyword if you enable full text search on a specified column. Okay, analyzer ASCII uses a custom analyzer called this. Okay, BM25 ranking algorithm and highlights. And then, oh wow, so there's literally nothing else to it. But I still don't know, can you define it on multiple columns? How do you define it on all the columns by default? That's the question. So vector search indexes, and that's gonna be for later. And M3 simple task finding exact nearest neighbors based on distance metrics. So again, this is probably, yeah, embeddings, yep. So we don't care about that. Navigable small worlds, so this might be another high dimensional spaces. And index utilization and queues, okay. Inquiry, sorry, we're building indexes and then a bunch of stuff. Concurrently building indexes can be lengthy. May time out before they're completed. Use the concurrently option to build the index without blocking operations. The statement will return immediately, allowing you to monitor the index building progress by executing the info statement. Oh, so that makes sense if we just define the index so that this is not something that will be impacting future queries or whenever we're adding something. This is just for the initial index definition because maybe we already have a table with, you know, several million records and we're defining some complex index, right? We just don't want it to hang for 2 minutes. So we can just concurrently just gonna finish in the background, and that's that. Okay, so that's that, and that's it. All right. So let me just look at this about the multiple composite index. The composite index spans multiple fields and columns of a table. Similar to a single field index, a composite index can also be unique. Okay, so in theory, I should be able to. Then we have like a example of index. Let's say that I want to M3 vector search. There we go. So let's say we define this analyzer, right? So that we have it. There's an analyzer. It already exists. So overwrite. Probably literally the same thing, right? So we have the analyzer. And we want to define an index on a table user. So let's say that we have a create table user schemaless. Okay. Run it. Wait, define. Oops. There we go. So we've got table and define index username index on table user columns, and we have the search analyzer this with everything. So maybe I want it on a name, on this whatever notes of the user, address, and maybe who knows, some other text field will be, I don't know, Intel. Can I make this? Yes, I can. So in theory, this index will allow me to search through everything, no matter the field. Although I don't know if it's gonna help me. Huh, so that's the question. This index, will it help me to search over all the fields at the same time and only when I'm searching over all of them at the same time? Or is it that I can search, let's say, only by Intel or something? I wonder if this kind of would work, but at the same time, it would make it not great. Something tells me this will be not great. So I'll need to ask about that. So let's do multiple fields. Multiple field index. That's the question I need to add on SurrealDB Discord to kind of figure out how that really works, because it's not very well described. But it's possible to define. Okay, so we did that. Now I guess we need to move on to the next part, which is the vector search. Because, okay, I understand full text search. I mean, didn't we also have the extra stuff like database functions, encoding functions? Do we have like the actual stuff for the string functions? The B, whatever, what was it? BM25. Reference guides using this. Search functions. So there is category search functions. Let's highlight offset score. But it doesn't provide us with actual details about the BM25. I guess one would need to just search what the BM25 is. So let's go here. What is the BM25 search? What was it? Search relevance algorithm. It should give us something, right? Wait, chat history. What? New. There we go. Best matching 25. Okay, that's what it means. Probabilistic ranking function used to estimate the relevance of documents of given search query. It's one of the most widely used algorithms in information retrieval and forms the foundation of many search engines. Okay, so I don't care how it works, but we have, maybe. BM25 calculates a relevance score for each document based on the query terms that appear in it. The algorithm considers several key factors. Term frequency, that's the TF. How often a query term appears in a document. However, unlike simple term frequency, BM25 uses a saturation function that prevents the score from increasing indefinitely as term frequency grows. Okay, so I guess it just tapers off to not overwhelm with it. And then we've got inverse document frequency, IDF. Terms that appear in fewer documents across the entire collection are given more weight as they're considered more discriminative. Okay, and document length normalization, longer documents are penalized to prevent them from having an unfair advantage simply due to their size. Okay, so basically how frequently this term shows up for a given text. And we have some formula and whatnot, so I'm not going to do that. So K1, typically 1.22, controls term frequency saturated. Higher values mean term frequency has more impact before saturation. Okay. And we've got B, which is typically 0.75, controls the degree of document length normalization. Value 0 means no length normalization, while 1 means full normalization. Okay. All right. So there's some balance. You can probably, if you have already a bunch of data, you can play around with your data, adjusting those values to get results that you actually want. Okay. So we have advantages, applications, and that. Okay, and this is our only choice. So at least we know that we can, it's standard things. So K1 and B, those two terms are the ones that we can control whenever we reach out to SurrealDB. Okay. So let's get rid of all those things. And let's go back, and we also have another thing, a vector. So finally, I'll start learning about vector databases, how they work. Exactly. So just give me 2 minutes. I'll be right back, and that's that. Alrighty, I'm back. Bam, bam. We can continue. Okay, so time for the fun part, which is vector search and whatnot. Basically, using SurrealDB as a vector database. A vector database is specialized for storing these high-dimensional vectors. These A vector database is specialized for storing these high-dimensional vectors and for efficiently performing queries such as nearest neighbor search or similarity search. Rather than searching on exact values or text-based queries, vector databases let you search based on semantic similarity. For instance, in a text embedding scenario, you can find documents that are semantically similar to a given query, even if they do not share the same keywords. But how do you think in a vector database? Unlike relational or document models, where the focus is on well-defined schemas and relationships, vector databases revolve around embeddings, numerical representations of objects like text, images, audio snippets, etc., in a continuous vector space. We're going abstract. You have to design data structures and queries to exploit these embeddings for similarity search or AI-driven retrieval. Okay, in this guide, you'll learn about the basics of vector databases, how they differ from other data models, and how SurrealDB, a multi-model database, can store and query vector data alongside documents, graphs, and more. Okay, so what are embeddings? Embeddings are typically dense vectors of real numbers that capture the semantic or contextual meaning of data. For instance, in natural language processing, NLP, a word or sentence can be transformed into a vector of length 128, 256, 768, or even more dimensions. The idea is that similar objects in meaning end up having similar vector representations, making it possible to compute how close they are in the vector space. Okay, so it's kind of, we can imagine that we have some kind of space, and let's say words that have that specific meaning are somewhere here. Something that has other meaning has somewhere there. It's just, uh, we can, as humans, perceive it as 2 or 3 dimensions. So can I just, let's go to Xcali draw. Okay. So let's imagine that right now we have some kind of space, right? Uh, so we basically have one dimension here and another dimension here. Okay, so we have like 2 dimensions. We don't know dimension 1, we just one thing, right? And this will be dimension 2. And I really should just change it up for the sake of the stream. And let's just zoom in. There we go. So we have those 2 dimensions, and let's say the words like evil, right, would be here, and maybe I don't know. The opposite of evil is, what was this nice word? Thing was the I need AI for that. I just blanked out. What is the opposite of evil? Just good isn't good enough. I think there's a D word referring, like, suggesting of godly nature, something like that. Something with D. Divine, there we go. Yes. So let's say we have the word evil here, and here will be maybe divine, right? So like that space, maybe this axis, this dimension will be morally evil or divine, right? And then you have something like bad here and good here. They're a little bit closer together because in some way they are a little bit more generic. Like evil and divine suggest like extreme cases, while bad and good are a little bit more generic. So maybe in that axis you have something, while then you have something like neutral, right? And you can imagine that those words then can have different groups. Maybe this will be godly, this will be, I don't know, devilish, right? All those things. And then really what happens with it, we will need to add yet another dimension. Like let's say let's turn it into a cube. Okay, we added some perspective to it, but that means that suddenly we could have yet another dimension that maybe changes those words into because this is all what, adjectives, and suddenly you have divinity, right? So this is how much of adjective it is. This is how much of a noun, how noun-ish it is. So you would have good, you would have goodness, right? Neutrality, and all those things, right? And in between, maybe you would have some kind of adverb or something, right? So even though I don't know that word exists, but within a single axis, you could have basically this going like this, right? And this translates to that, just in different axes. And because we can correlate all those words in so many ways, each way that we can kind of correlate words is a different dimension. But suddenly, in our human imagination way, we can't perceive another dimension because we're kind of limited to visualize only 3 dimensions. But you can go forth and just, these are just kind of layers of how we can correlate words. And what it suggests is that you often have like 128 dimensions or maybe 768 different dimensions or different ways how those words correlate to each other. Therefore, words can be localized differently, right? And that kind of conveys the meaning, I guess. The more dimensions you have, the more precise your meanings get. So that's interesting, and you can kind of figure out that, okay, this sentence has groups. Those 2 sentences have groups of words that are in similar places that probably means the same thing. And that's that. So why store embeddings? Embeddings enable a range of powerful use cases. Semantics text search retrieve documents similar in meaning to a query, regardless of exact keyword overlap. Recommendation systems suggest items, movies, products, etc., similar to what a user has liked based on learned embeddings. Image or audio search identify images or audio clips semantically similar to a given sample. And Tarsus's head just exploded. A different way to think about the problem, right? Completely different. Saturday night mind duck. Yep, absolutely. So yeah, that's why world is going crazy about it, because suddenly not only you can store them and do things, you can actually use AI that kind of natively understands those meanings, and that's where fun begins. And clustering and classification performs unsupervised clustering of data points or quickly identify which category a vector is close to. When these embeddings need to be indexed and queried at scale, a specialized data structure, often called an approximate nearest neighbor (ANN) index or vector index, becomes necessary. This is where vector databases come in. Core concepts of vector-oriented modeling. All right. When transitioning to a vector database, you need to adapt your mindset to revolve around embeddings and distance metrics. So when I hear distance metrics, that means that probably, so when I go back to this example here, right? So a distance from good to bad could be in this specific dimension, right? But maybe good is a little bit more in that there, so you kind of have a diagonal line, right? So considering you have so many dimensions, you kind of need to get the shortest distance considering all the dimensions. So this is like pure mathematics because we can't imagine it. And that's how closely they, I guess, correlate, because each dimension will add some kind of distance to things. Okay, all right. So something like good and bad at the end of the day will be probably very close to each other because they'll be in some kind of abstract cluster of words that describe, the morality or something, or how good something is, right? So many similar things that they represent, and they're often tied together as, like another dimension could be how much of a what's the opposite of synonym? Antonym? How much of an antonym words are, right? So you have just so many distances to add up. Oof. Yeah, you definitely want hardware acceleration on that. Yeah. So distance metrics, yeah. So embeddings, each data item, a text document, an image, a user profile, or an event might be represented as a high-dimensional vector. These embeddings are often produced by machine learning models, like a transformer for text. Similarity metrics. Vectors are compared using a distance or similarity metric, such as cosine similarity, dot product, or Euclidean distance. Okay. Nearest neighbor search. The most common operation is to find the k nearest neighbors of a query vector. Rather than matching on keywords or IDs, the system retrieves items that have minimal distance from the query in the vector space. Okay. So yeah, basically, what are similar statements in this thing? Okay. Hybrid approach. Some queries combine classical filters, for example, a user's location or a date range, with vector similarity. This means you might need a system that can do both vector-based filtering and typical attribute-based queries, ideally in one seamless environment. There you go, SurrealDB. So SurrealDB as a vector database. Although SurrealDB is commonly discussed for its multi-model capabilities, supporting documents, tables, and graph relationships, it also has the ability to store and index vectors. This makes SurrealDB a powerful one-stop shop. If you need your document graph capabilities for typical data interactions, plus a vector search to power semantic queries, AI recommendations, or advanced content retrieval. With SurrealDB's SurrealQL, it can define vector fields, store numeric arrays as embeddings, create indexes, and perform similarity queries. SurrealDB's approach aims to unify these features so you don't have to maintain separate data stores. For example, a dedicated vector database plus a separate document or GraphDB. If you prefer a single integrated system. Exactly, just simplifies so much for you. So yeah, unless you have who knows how large system where it makes sense to have very specialized databases, go SurrealDB. Okay, so this is just like a little, marketing overview, but it gave us some idea. So we have vector search cheat sheet, SurrealDB vector search, vector functions, YouTube, and vector search indexes. What the hell is YouTube? Oh, it's just a video. Okay. So let's skip that. We don't want to watch a video right now. Vector search indexes, vector functions, SurrealDB vector search. So what is a cheat sheet? Cheat sheet is just a cheat sheet. So this, what is a cheat sheet? And yeah, this doesn't give us much info right now. So let's look at vector search. Okay. Maybe this will be a more decent introduction. Vector search. SurrealDB supports full text search and vector search. Full text search involves indexing documents using the full text search index and breaking down the content of the document into smaller tokens with the help of analyzers and tokenizers. Vector search in SurrealDB is introduced to support efficient and accurate searching of high-dimensional data. This guide will walk you through the essentials of working with vectors in SurrealDB, from storing vectors in embeddings to perform computations and optimizing searches with various indexing strategies. So one thing is that, how do you get those vectors? How do you get those embeddings in the first place from a text, for example? That's probably where specialized AIs will come in that actually take in your input and produce vectors, and then you need to use the same AI to kind of extract the meaning to back into what it was if you want to do something more with it. But often you can just use it to turn into vectors, and then you can do your searches there at that point. Okay. So what is vector search? Vector search is a search mechanism that goes beyond traditional keyword matching and text-based search methods to capture deeper characteristics and similarities between data. It converts data such as text, images, or sounds into numerical vectors called vector embeddings. You can think of vector embeddings as cells, like how cells form the basic structural and biological unit of all known living organisms. Vector embeddings serve as the basic units of data representation in vector search. Okay? Vector search isn't new to the world of data science. Gerald Salton, known as the father of information retrieval, introduced the vector space model cosine similarity, and TF-IDF for information retrieval around 9060. Okay. Yeah, I guess. Yeah. There you go. Nothing new. If you're interested in understanding vector search in depth, check out this academic paper on vector retrieval written by Sebastian Bruch. We're not going there. It's very likely way over my head. I'm bad with math. Like, yeah, no, thank you. Not my kind of content. That's probably something for you, Taras. You would probably have easier time understanding that. Vector search cheat sheet. So, wait, not cheat sheet. Oh. It's the same thing. Both links are to the same thing. Okay, so, yeah, sure. mtree. When you need the exact nearest neighbor, you just go with mtree. Okay? HNSW, efficient approximation for high dimensions of large datasets. So I guess this is for larger datasets, while this is for a very specific thing. And brute force, when you don't define an index or you want exact nearest neighbors, or when you provide a distance function to the query. So you can kind of brute force it instead of having pre-compute or something. Interesting. So mtree index, we have the dimension, which is the size of the vector, distance function, the vector type. Okay, so we have floating 64, floating 32, integer. Okay, I see. So like precision of the vector. Then we've got capacity, max number of records that can be stored in the index, and order, and mtree cache, and whatever. I'm not even reading that right now. It's just how to define it in the index. Okay, then we got the HNSW. What browser am I using? This is Zen browser because Arc, I believe, just died. And I was using it purely for streaming. So now I switched to Zen. I would like to use Zen for my personal stuff, but I find it kind of laggy, especially Google website for some reason are really chugging and slowing down. I'm getting occasional errors. It's based on Firefox, so maybe that's why. I don't know, but yeah, I really like this. I really like all the fun features. Just the fact that the top bar hides, the left bar I can make hide, and I can still split stuff, but at the same time it's laggy, so I'm not using it for day-to-day stuff. But for a stream where I'm just reading some stuff, it's great. All right. So this thing again, we have dimensions, distance, function, vector type, some EF construction, and more connection layers and whatnot. No idea. Okay. So we can define those indexes again. And users are strongly suggested not to set an LM value, as it is computed based on other parameters. Only users completely versed in the field should manually set it. Huh. Okay. So we have querying, right? So we define the index. We have some stuff there. So we have our vector of like 2, 3, 4, right? And we select ID and vector distance. What nearest known neighbor? KNN, known nearest neighbor, as distance. So distance from vector. And we basically get our points. Select ID and the distance is distance and point. Something like this. Return to, in this case, using the distance function defined in the index Euclidean between something and a vector. I have no idea what's going on here. And this is just a cheat sheet. I guess we'll get a little bit more here. Oh, geez. So we have select functions. We have basically various, again, ways to get similarity, distance, and stuff, right? Okay. Then we have where statement, which is this is uses distance function to find an index. What is the number 2 in there? Euclidean, brute force method, cosine, Manhattan, and all that stuff. 2 to 10. Invalid only for H and SW. Second parameter is effort. So it's some kind of parameter that goes into the function, I guess, that compares stuff. So much for good explanation, right? I've got notes, verify index utilization and queries using explain full clause or point something number 10 with this vector explain full. Great. P values, more about P for Minkowski distance. So I guess this is it. No, 2 to 0 is Manhattan diamond, Euclidean circle, squircle, or square. What? Vector search versus full text search. This is not the greatest explanation, it's just random cheat sheet. The image above, I guess maybe it's just targeted for people who actually know what this is, and it's like, oh, it's like that, and they can just move on. But I would like an easier access to actual explanation. And CPN says, I just want a normal browser with tabs on the side. Yeah, that's exactly. So I might try this, and CPN is going. So see you, CPN. It's nice having you here. Okay, so lead or lead, right? So the lead here shows lead or cause person or animal. Then you have a root of means of access. Be a root or means of access to a particular place. Oh, the door led to a long hallway. And you have a noun, the initiative, an action, or a position of advantage in contest. Have a lead, right? Have the lead. The image above is a Google search for the word lead or lead. The search has pulled up different definitions of the word lead. Lead can take initiative as well as the chemical element of the symbol PB. Now let's add some context to the word. Consider a database of liquid samples which note down harmful chemicals that are found in them. In the example below, we have a table called liquids with a sample field and a content field. Next, we can do full text index on the content field by first defining an analyzer called liquid analyzer. We can then define an index on the content field in a liquid table and set our custom analyzer, liquid analyzer, to search through index. I already see where they will lead with that. Then using the select statement to retrieve all the samples containing chemical lead, we will also bring up samples that mention the word lead or lead, right? Liquids, sample, whatever. So we have insert bunch of stuff, right? Define analyzer, yep. And we select stuff. So we can just execute the query. Well, the seawater contains some amount of lead. So that's great. The team led by Dr. Rose found out that the tap water in was potable. And suddenly that's a false one, right? Because, yeah, because that's not it. Amounts of A were found in sewage water. A? What? How does that contain lead? Unless letter A makes it? What the heck? Strange. So if you read through the contents of tap water sample, you'll notice that it does not contain any lead in it, but it has the mention of the word lead under the team led by Dr. Rose, which means that the team was guided by Dr. Rose. The search pulled up both the records, although the tap water sample had no lead in it. This example shows us that while full-text search does a great job at matching query terms with index documents, it may not be the best solution for use cases where the query terms have deeper context and scope for ambiguity. So then we have vector search in SurrealDB. There we go. We have some kind of space and those vectors are in it. The vector search feature of SurrealDB will help you do more and dig deeper into your data. For example, still using the same liquids table, you can store the chemical composition of the liquid samples in a vector format. So insert into liquids vector, and we insert feels like sample, seawater content. Seawater contains amount of lead, embedding, and I guess we already got the embedding, right? And we have another one with another embedding and some other embedding. Notice that we have added the embedding field to the table. This field will store a vector embeddings of the content field so we can perform vector searches on it. You have the options of using 3 different approaches for performing vector search. Brute force, hierarchical, navigable, small world. That's a fun name. Small world. Or M-tree. As you want to perform a nearest neighbor search and not an exact search, you would typically use an index like HNSW or M-tree. So we have lead harmful. So add embeddings for what lead as a harmful substance should be. So we have an embedding of the meaning of lead as the harmful substance, right? Not anything else. And this is represented by, let's see, those numbers, right? Define a vector index on the liquid vector table for embedding field. And we have index, 4 dimensions, type F32, right? Select a sample, the sample and content from the liquids table with cosine similarity. So we select this and do that. So I guess we need to, that's not it, right? Where were the embeddings added? Here, but we don't have that. So maybe this already contains the data, I guess. So we run it. And yeah, it created those. And the seawater contains some amount of lead. High amounts of A were found in sewage water. And there we go. And we don't have that other thing in there anymore. So we have actual distance provided. So which number is better, higher or lower? Don't know. But this suggests, I mean, we sort it in some way. Select this, don't sort it. So I don't know. Don't know. But this is interesting. What if I'll just comment this out and do select everything from liquids vector, right? Let's also comment those out. I will select everything. So we literally have 4 dimensions for embeddings, and somehow this contains info if this is similar to lead or not. Wow. That's actually fascinating that during using those 4 numbers we could do that. Huh. What if we already have the index, right? So I mean, so let's uncomment this and uncomment the search. What if I'm gonna change this embedding from 25 to from 15 to 25? That's probably a drastic change. I expect token and identifier, comma. Oh, run. So it still found lead, with same confidence. Confidence? What if I'm gonna change this to 25? What if I'm gonna change it completely to 15? This will be to 55, and this will be to 75. Oh, now it's search for something else. We don't know what for. Oh, that's fun. That's actually really fun, huh? That's how probably people start exploring those spaces, how things are related to each other and whatnot. This is fascinating. In the example above, you can see that the results are more accurate. The search pulled up only the seawater sample, which contains the harmful substance lead in it. This is the advantage of using vector search over full text search. Another use case for vector search is in the field of facial recognition. For example, if you wanted to search for an actor or actress who looked like you from an extensive data set of movie artists, you would first use a machine learning model to convert artists' images and details into vector embeddings, and then use SurrealQL to find the artist, with the most resemblance to your face, vector embeddings. The more characteristics you decide to include in your vector embeddings, the higher the dimensionality of your vector will be, potentially improving the accuracy of the matches, but also increasing the complexity of the vector search. So yeah, this is an example that is kind of easy to imagine where, let's say, like in a video game, you create a new character, you need to decide on a face, right? You have a bunch of sliders, like, how far apart eyes are, how large they are, how, the shape of lips or position of the nose, right? All the sliders. So each one is the vector dimension, and therefore the set of all sliders is that one embedding. And you can put all those faces in there and therefore compare which ones are close to each other to find similar faces. So when you think about it, it's really, really obvious. But what is not obvious nowadays is that those machine learning models or AIs, they don't make those sliders as obvious as like, oh, the slider will be just for how far apart eyes are. The slider will be probably describing something abstract to us, or maybe it will end up being something useful, but we don't know, and we at this point we don't have to know. As long as we can apply the same model to all the faces, we're gonna get the similarity. Okay. So now that you know how to handle vector search query in SurrealDB, let's take a step back and understand some of its terms. I mean, I don't understand this. What the heck is this? Number two, what if I'm gonna, first of all, refresh the page to reset everything, right? And we have this thing. I run it and it's found it. What is 2? What if I'm going to change it to 3? Change the results. What is this number? I don't understand. It's not explained anywhere. So how to store vector embeddings. To store vectors in SurrealDB, you typically define a field within your data schema dedicated to holding the vector data. These vectors represent space data points and can be used for various applications, from recommendation systems to image recognition. Below is an example of how to create records with vector embeddings. So create document 1, content, we have items, this, and this is literally an array of numbers, and that's it. But how do you type it in your schema? The vector is represented as an array of floating point numbers. There are no strict rules or limitations regarding the length of the embeddings, and they can be as large as needed. Just keep in mind the larger embeddings lead to more data to process, and that can affect performance and query times based on your physical hardware. So computation on vectors. So vector package of functions. So SurrealDB provides vector functions for most of the major numerical computations done on vectors. They include functions for element-wise addition, division, and even normalization. They also include similarity and distance functions, which help in understanding how similar or dissimilar two vectors are. Usually, the vector with the smallest distance or the large cosine similarity value closest to 1. Okay, so closest to 1, that's what we're looking for. Okay. Is deemed the most similar to the item you are trying to search for. So Euclidean is basically the actual distance. Cosine is basically direction-wise. Okay. Hamming is binary-wise. Okay. Manhattan is just, two of those, whatever. Minkowski is Manhattan is 1, Euclidean is 2, and infinity is 1 dimension. Okay. Chebyshev is 1 dimension. Okay. Jacquard is more complicated, and PCC is based on trends, I guess. Or maybe it tries to find some kind of linear function around it. Interesting. The choice of distance or similarity function depends on the nature of your data and the specific requirements of your application. So this is kind of fun because when you grasp the idea and what you can do with that, suddenly you have so many toys to play with. And it'll be kind of fun to know when to apply which. So that's kind of fun thing, but not the focus now. In the liquid examples, we assume that embeddings represent the harmfulness of lead as a substance. We use the vector similarity cosine function because cosine similarity is typically preferred when absolute distances are less important, but proportions and direction matter more. Oh, look at that. So not the absolute distances, but the proportions and direction. Interesting. Interesting what those words can mean in context of some kind of meaning, right? Hmm. So vector indexes. And notice that we haven't had a single word about how to generate embeddings. Just not mentioned at all. So vector indexes. When it comes to search, you can always use brute force. In SurrealDB, you can use the brute force approach to search through your vector embeddings in data. Brute force search compares a query vector against all vectors in a dataset to find the closest match. As this is a brute force approach, you do not create an index for this approach. Okay, so basically, with all those examples so far, whenever we add content, we already have index defined that will kind of calculate the stuff around things, right? What the kind of distances and whatnot. And if you don't have specific thing or you just never bother with that for those, maybe you have large set of data or like not large set of data, but you have data and you need to prioritize that you don't have any indexes or something, just quick entry or something. And occasionally, very rarely, you need to do something and it doesn't have to happen fast. You can just brute force. Sure. The brute force approach for finding the nearest neighbor is generally preferred in the following use cases. Small data sets, limited query vectors. For applications with small data sets, the overhead of building and maintaining an index might outweigh its benefits. In such cases, the brute force approach is optimal. Guaranteed accuracy. Since the brute force method compares the query vector against every vector in the dataset, it guarantees finding the exact nearest vectors based on the chosen distance metric, like Euclidean, Manhattan, etc. And benchmarking models. The brute force approach can be used as a reference and help benchmark the performance of other approximate alternatives like HNSW. Okay. While brute force can give you exact results, it's computationally expensive for large datasets. In most cases, you do not need a 100% exact match, and you can give it up for faster high-dimensional searches to find the approximate nearest neighbor to a query vector. Okay, so it's an approximate nearest neighbor, okay? So that's interesting. We don't always get the absolute best match. We just get something roughly there. Okay. This is where vector indexes come in. In SurrealDB, you can perform a vector search using two primary indexes. The M tree. Wait, they're repeating the same stuff again? The M tree is a metric tree-based index. Okay, metric tree-based index. Now we know what it means. Suitable for similarity search in metric spaces. Okay. And the M tree index can be configured with parameters such as distance function to compare the vectors. Okay. Now we have the hierarchical navigable. English is hard today. Hierarchical navigable small world index. So HNSW is a state-of-the-art algorithm for approximate nearest neighbor search in high-dimensional spaces. It offers a balance between search efficiency and accuracy. The HNSW index is a proximity graph-based index. Okay. By design, HNSW currently operates as in-memory structure. Ooh. Introducing persistence to this feature, while beneficial for retaining index states, is an ongoing area of development. Our goal is to balance the speed of data ingestion with the advantages of persistence. Interesting. So you don't want it on a large data set, I guess. Huh. So you can also use the rebuild statement, which allows for the manual rebuilding of indexes as needed. This approach ensures that while we explore persistence options, we maintain the optimal performance that users expect from HNSW and M tree, providing flexibility and control over the indexing process. So both indexes are designed to handle the challenges of searching in spaces where traditional indexing methods become inefficient. The choice between HNSW and M tree would depend on the application-specific requirements, such as the need for an exact versus approximate nearest neighbor search, the distance metric used, and the nature of the data. So this is very interesting how to actually do that. So HNSW, I guess, is a better approach, possibly faster when doing the search, while this one is persistent. So our index just, is there saved. So when we restart the database, we don't lose the index. So filtering through vector search, the vector distance KNN function from SurrealDB returns the distance computed between vectors by the KNN operator. This operator can be used to avoid recomputation of the distance in every select query. Consider a scenario where you're searching for actors who look like you, but they should have won an Oscar. You set a flag, which is true for actors who've won the Golden Trophy. Let's create a data set of actors and define an HNSW index on the embeddings field. Okay, so that's exactly what I'm thinking about, because in case of the crude search that I want to implement, in theory, I could have a table for all the data, right? So I have all the indexes and analyzers defined once, but I want to store data from multiple customers, right? So I would have a field like the user ID. And my indexes, I don't really want them so that I'm searching for a term and I'm suddenly getting data from all the customers. I want to search just through this specific customer, but still have benefits or searching through vector space. So yeah, I wonder how that works. So you need to be running SurrealDB version 2.0 or higher to use the vector distance KNN function. So create a data set of actors, embeddings, and flags. So we create actor 1, right? We have the embedding and a flag, for example, true. This is false, true, true, right? So this one will be ruled out. Define an embedding to represent a face. So this is like, the specific face for what we're looking for, right? Then define an NSW index on the actor table. So define index on actor on a field embedding, right? And it'll be HNSW for dimensions because that's what our data is. And then select actors who look like you and have won an Oscar. So when we do the select statement, we want to get their ID, the flag, and the distance as distance, right? So from actor, so we do where the flag is true and an embedding is whatever that means, 240, whatever. Still don't know what that means. But I guess the overall, this thing in those little brackets is like some kind of vector search. And then we also want to order them by distance, as in by similarity. Okay. So basically we get this and that, and these are true. So this one was rejected, while probably one of them, like this one, was rejected completely as well because it was too dissimilar, right? Actor 3. Yep, this one was rejected. Okay. So actor 1 and actor 2 have the closest resemblance with your query vector and also have one Oscar. One Oscar. Number 2. No, 1 and 4. Oops. Okay, so that means that the vector function returns a distance computed between vectors. This operator can be used to avoid recomputation of the distance in every select query. Still don't know what that means exactly. It caches it somewhere? The vector distance function returns the distance in query by the KNN operator, avoiding recomputation. So shows a function output. So we do stuff, we get stuff back. And that's it. What does it mean, avoiding recomputation? Don't know. Great. So now we have random conclusion. Vector search does not need to be complicated and overwhelming. Once you have your embeddings available, you can try out different vector functions in combination with your query vector to see what works best for your use case. As discussed in the reference guide, you have 3 options to perform vector search in SurrealDB. Based on the complexity of your data and accuracy expectations, you can choose between them. You can design your select statement to query your search result along with filters and conditions. In order to avoid your calculation of the KNN distance for every single query, you also have the vector distance KNN. Whatever. Due to GenAI, most applications today deal with intricate data with layered meanings and characteristics. Vector search plays a big role in analyzing such data to find what you're looking for or to make informed decisions. You can start using vector search in SurrealDB by installing SurrealDB on your machines or by using Surrealist. And if you're looking for a quick video explaining vector search, check out our YouTube channel. Okay, so we still don't have answers to how to create embeddings. And I assume that we just do it externally outside of SurrealDB. Otherwise, they will be already talking about it. So embedding. Oh no, that's just to embed SurrealDB inside your program, inside your software. Like you embed it right in JavaScript in a browser or in Rust or in .NET. Look at that. SurrealDB is designed to be run in many different ways, environments. Huh, that's fun. Okay, but what's labs? Oh, look at that. Do we have anything? Topic? Oh, we can't scroll down. Wow, okay. Embedding. There we go. SurrealDB as vector store for LangChain. Ugh, LangChain. It's SurrealDB vector store for LangChain. Use SurrealDB with LangChain. Everything is with LangChain. What is deals to? Okay, so this is like an example project. LangChain SurrealDB. Okay. All right, installation, and we basically have an example, and this is what code? Python. Oh, okay. So let's just ask here. New chat. I have access to a vector database. How do I get embeddings for my content? Hmm. First thing Claude suggests, OpenAI. So there's several ways to generate embeddings for your content depending on your specific needs. Using OpenAI's embedding API, the most straightforward approach is OpenAI's text embedding models. And we have Python examples, so we basically go client, our API key, and create. So model will be text embedding 3 small. So basically, there are specific AI models for generating embeddings, and this is my text. And we get embeddings. Other embedding APIs, Cohere offers multilingual embeddings via their API. Anthropic, Claude doesn't currently offer embedding endpoints, but you can use other providers. Okay, makes sense. Google, Vertex AI, Azure has its stuff, or self-hosted options like sentence transformers and other popular models. Okay, all right. Considerations: content preprocessing. Clean and chunk your text appropriately. Most embeddings models work best within 200 to 500 tokens per chunk. Okay, so that's something I heard about that, in theory, because we create one embedding, which is like one place inside the vector space that basically explains some kind of meaning, right? Therefore, if we have entire article, in theory, we could create an embedding for this entire article that just gives on one point in some super high dimensional space that this is the exact meaning and all the meaning of that specific article. Therefore, we could, in theory, search for articles that have very similar content, right? But most of the time, we don't want to do that because A, our vector space will be massive, like so many dimensions, gigantic embeddings. And second, we just, that one spot, the vector embedding is kind of approximation of the meaning. It's not the exact meaning, it's just approximation. So if we want to approximate entire article, which is so many points, so many things that article tries to represent, right? Maybe entire process, we just combine it into a single point that's kind of missing the point. So you want to like intelligently split the article into various parts that represent specific meanings, right? Maybe one is saying that, hey, there is this thing and it means this. And then another part would be that this thing is used for that. Another one that this thing is also used for that. And then maybe another one is that your first step to do this kind of plan is this. And then, you have those little chunks for each for which you can create embeddings, right? So you end up with multiple smaller embeddings. Therefore, you can search through multiple of them and find that, maybe I'm looking for an article about this. And we found one article that has, you know, 5 embeddings that match this thing that you searched for. So we know that, okay, this article is a really good match because it has several strong matches to what we search for. Okay. So model choice, consider factors like embedding dimension. Higher is more expensive but more storage. More expressive but more storage. Yeah, so more dimensions means that we kind of better encapsulate the meaning of the text that we provided to it, right? But at the same time, we just have more dimensions, so it takes up more storage and it takes up more, you know, we need more calculations to maybe do comparisons and other stuff, right? I'm going to support domain specialization. I guess there are models that are trying to specialize in better vector creation for different things. Cost and latency. Batch processing. Most APIs support batching multiple texts into one request for efficiency. Now, what type of content are you working with? And do you have preferences for hosted versus self-hosted? Yeah, that's a good question. How expensive is it to run it? Let's say that I want self-hosted solution, mostly for um, creating embeddings for short articles, uh, e-commerce, product descriptions, etc. How how computation heavy are those self-hosted solutions? I only have a mere NVIDIA. What is it? GeForce 3080 Ti. That's what I have. So not a lot of VRAM. So I just wonder because maybe I could self-host it and for like testing. It's actually quite capable for self-hosted embedding generation because I believe embedding generations are not as heavy as like big LLMs. It's like very cheap compared to that. It has 12 VRAM and solid compute performance, which should handle most embedding models well. So sentence transformers will work great. Sentence transformers. Oh, but it's in Python. I mean, it uses CUDA. Okay. Let's check if CUDA is available for batch processing, this and that, and it just spits out embeddings, right? That's fun. So in your case, for e-commerce articles, these work well. All many LM L6v2. So we have 384 dimensions. So okay, 80 megabytes, very fast. This is better quality, good for search retrieval. Oh, I want search retrieval, yeah. Okay, wow, so many things to explore. Performance estimates. So I would have 1,000 to 2,000 short text per second. Okay, so I can do that easily. All right, VRAM usage less than 1 gigabyte for the model, perfect for product descriptions, typically 50 to 100 words. With this one will be probably 800 to 500, 800. VRAM usage 2 gigabytes. Oof, better semantic understanding. Okay, so this could be fun to just have that. Okay, let's self-host a little embedding thing. And I could probably game and have some things generated for me over time. Because I'm thinking like, somebody wants to upload, I know, 200 descriptions. If I can do, let's say 500 per second, that's not a big deal. Okay. For initial time self-hosting, sure, especially that those embeddings don't have to be created immediately. They can be added after the fact. All right. I like that. Optimization tips, batch processing for efficiency. I guess it just doesn't have to warm up the whole thing. Or whatever. Memory management can easily handle multiple embedding models loaded simultaneously. And whatever. Okay. We set up? Not yet. So next thing that I would want to know is how, because, creating the embeddings seems to be easy. You just hand it off to that AI model, and it would just spit out the embedding, right? But now how to do the chunking? How do I approach splitting slash chunking my content to hand off for embedding generation? Let's say that the articles I'll be handling, you have two to maybe 5,000 words. Um, maybe not words, characters. Okay. Um, I also want to self-host this process, and I want the chunking to be somewhat smart to not lose semantic meaning. Right? Something of this sort. I guess you could do some overlap and stuff. So for articles, 2,000 to 5,000 characters, you'll want a semantic aware chunking that preserves meaning. Here's how you approach it. Smart chunking strategies. Sentence aware chunking. Recommended for articles, right? So you can import, you have sentence transformer, smart chunk by sentences. So respecting semantic boundaries. So how does it chunk? For sentences. How do I NLTK, which is some package sent or sentence tokenized. Okay, so there are things that will recognize that these are sentences. Okay. So we have for those, if adding this sentence exceeds max size, finalize current chunk, create overlap by keeping last few sentences. Okay, so we do some overlap so that those things are not too disjoint. Few sentences. Wow, that's what is a few? Okay. Add final chunk. Okay, so this is relatively simple code, nothing this great here. Semantic chunking, most advanced. So we have sklearn metrics pairwise, cosine similarity. Oh. So we get a model, semantic chunk. So we basically get sentences, then get embeddings for all sentences. So I basically will embed everything twice. The embeddings for sentences, and then I kind of combine them to see how similar they are, join them, whatever. Ugh. Paragraph aware chunking, good balance of speed and quality. I would probably do sentence wise, yeah. Okay, great. Complete processing pipeline, great. So for your case, for 2,000 to 5,000 characters articles, I'd recommend chunk size 400, 600 characters, roughly 1-2 paragraphs. Overlap. Methods start with paragraph aware chunking. Okay, paragraph aware approach will most efficient on. Yep. Uh, what if I need to handle both short and long text in one workflow with one embedding model? My vector DB will have a table with which combines various data types. Let's do short product descriptions, maybe some kind of titles, articles. What else could people throw in there? SEO descriptions, recipes, etc. I will need to generate embeddings for all of them, no matter their length. Let's see what it suggests. I'm just curious because I think with this sentence base would be good enough. For unified workflow handling diverse content, you'll need an adaptive chunking strategy that intelligently handles each content type. Here's a comprehensive approach. So adaptive, so I guess it would just make decisions on content length, right? So content type configurations, so product description. Okay, so I would need to basically specify the chunk size, all that, article, SEO description, right? Preserve whole, paragraph aware. Yeah, so for something like product description, it would probably prefer to preserve entire embedding just to have an idea of the product, right? Title, preserve whole. For articles, it would be nice to be like paragraph aware. For for preserve whole, recipe aware, sentence aware. Yeah, there are so many ways to categorize that, but I think I have ideas to just make it simple, the crude, but working somewhat. Okay, browse content, in text, all that stuff, generate chunks. Mm-hmm. Let's be a word chunk and all that fun stuff. Gosh, that's lots of code. Usage examples. Okay, no matter. So adaptive sizing, content aware, consistent embeddings, metadata preservation, and batching, and great. Okay, so we know that we need to take in the data, split it into those chunks, generate embeddings for that, and then I guess we would need to have multiple embeddings per something in a database. Yeah, I guess. So SurrealDB so far was suggesting that, okay, for each record, you just have one embedding, right? And that's how you can do the index and whatnot. So I think this would need to be split where you have the content and then you have a bunch of embeddings that point to it. So that for an article, we could have, 15 separate embeddings, and that's that. Yeah. Okay. I can see that working. I'm just, processing to make the product work. Trying to think of it. So yeah. So that was it. And for Serial Labs, we just have everything with LangChain. I don't want anything with LangChain. Why is that? Let's just go to AI. And I saw something about RAG. Build an AI RAG agent. Is there something else about RAG? Example of RAG using SurrealDB and OpenAI. So I guess OpenAI for embeddings. Oh. This project aims to demonstrate the potential of integrating SurrealDB with OpenAI by importing 25,000 Wikipedia articles complete with vector embeddings generated by OpenAI. The ultimate goal is to develop a retrieval augmented generation RAG question answering system. The backend is powered by a fast API server with Jinja 2 handling template rendering, so it's all Python, okay? Getting started, SurrealDB, ensure that SurrealDB is installed, Python 3.11, SurrealDB SDK, clone the repository, you will need OpenAI token, yes, setting up, and Python environment, blah, 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 and that's it. So it doesn't show anything. Okay. Oh, well. What do we have? Source. I guess AppPy, initPy is nothing. AppPy. Extract ID, convert timestamp to date, lifespan, interesting, fast API, and all that stuff. You know what? Let's do this. I'm gonna. Oh, this is yeah. Sort of be OpenAI. Let's just clone it. All right. I'm just gonna go here. Let's go to Ubuntu. All right. Let's just make it a little bit larger for the stream. Repos. And let's do git clone and this thing here. Okay. Okay. And this is RealDB OpenAI. And let's do Claude. Please familiarize ourselves with the project. And let's just let it process things quickly. This way we can just ask generic questions rather than me thinking in Python. I'm not that familiar, haven't done anything in years in Python. So, well, I need overall answers like how do they handle chunking and all that stuff. If they do that, because they, in theory, if they want to do something like RAG, they are probably splitting it, generating embeddings, how it's formatted in SurrealDB, I wonder, and then how they're actually retrieving the content. Haven't done anything with RAG, haven't really watched any theories of how it's supposed to work, but maybe we can just explore it quickly so that I can get some answers. Okay, this is taking time. I'll be right back. I'll just blow my nose. Alrighty, so while this is thinking, let me actually start writing another, prompt. Now I want you to. Okay, so what do I have here? Core functionality imports articles. User can ask questions. The system found relevant. This generates contextual answers based on the retrieved articles. Yeah. Oh, because RAG will be that we take the embeddings, probably turn it from embedding to text descriptions, hand them off to larger AI that can kind of comprehend it and explain it. Okay, that's what I expect how it works. So backend is Python, frontend, database, AI. Demonstrate modern RAG, retrieval architecture, vector databases, and LLMs. I want you to focus on the backend / database for now. I want to understand how the articles are turned into embeddings and how they're stored in SurrealDB. Let's start with that. So, okay, it's gonna examine the database schema and wiki embedding table, understand data, blah, blah. Okay, so it's going. So I expect that there will be some kind of, once an article is downloaded, it will probably chunk it, turn it to embeddings using OpenAI, probably have a table of all the embeddings that they point to an article, and then and that will be it, probably for storing data. That's at least what I would do, unless there's some missing point that I'm hoping to find, something that will be like, oh wow, that's a good idea. It tries to find the actual content. Doesn't matter. Okay, now it's writing a description for us, I guess. Come on. Auto update failed. Right. Okay, so let's see what's going on here. So first, per computer embeddings from OpenAI. The embeddings are not generated by this application. Instead, OpenAI provides the pre-computed data set. Vector database Wikipedia articles embedded.csv. Oh, so somebody went and just straight up did all that work so that we already have embeddings, right? Embedding model, text embedding ADA 002. Okay, 1536 dimensions. So something tells me they have one embedding per article. Ooh. Contains URL, title, text, title vector, and content vector columns. So the wiki embeddings table structure: URL, title, text, title vector, and content vector. Title vector has also 1536 dimensions. Okay. I don't think that's required for a title. Could be optimized. All right. So they're just going easy route. Vector index configuration. SurrealDB uses M3 index for efficient vector search. Yep, they define embedding and do all that stuff. And M3 dimension, there you go. Okay, data import process. Chunk processing reads CSV in 100 record chunks to manage memory. Okay. And it's just parses vector strings using, okay, because we need to turn it into actual numbers, escape special characters, formats records, and bulk insert 100 records at a time using WebSocket connection. Okay. And then runtime embedding generator. While article embeddings are pre-computed, user queries are embedded in real time. Complete, yeah, embedding model, string, whatever. This function calls OpenAI's API to generate embeddings for user input during searches. So each embedding send to, OpenAI sends you back the, again, 1536 dimension vector back, and you send it to the database, and bam. So that's when, yeah, okay. All right. So that makes sense. And the search process, when searching, the system embeds the user query using the same model. Uses SurrealDB's vector operations. And calculates cosine similarity scores. Returns the most similar document if above threshold. Okay. Considering that the articles are represented by a 1536, right? Mention vector. One embedding per article contents. It means that they didn't bother with chunking. How accurate is the whatever 1536 dimension vector for something as long as long what the hell of this, as long as, gosh, I'm getting tired, as long as a Wikipedia article. I feel like with chunking, right? With chunking they could go, they could do away with less dimensional vectors. What's your opinion? Yeah, because I guess you could do just one large thing and just be done with it, right? I wonder what the price is for something like so. While this is thinking, I just want to go to something like OpenAI models pricing API. API pricing. We have just GPT. We don't want that. We want embedding. Okay, that wasn't helpful. Embedding models. Platform. Oh, there we go. Text tokens, audio tokens, fine tuning, built-in tools, transcription, text speech, image generation, embeddings. There we go. So we had text embedding, 3 small, 3 large, and ADA 2. So they went with the 10 cents per million tokens. Okay. I mean, it's not that much. And something like text embeddings 3 small is 2 cents per million tokens. So yeah, I wonder how much data would that be and what kind of embeddings they're producing. Hmm. Interesting. Interesting. There's other ones, and yeah. Gosh, that's expensive for something so old. Omni moderations latest, text moderation latest, they're free. Interesting. Okay, so let's see what this did. Fetch. Uh, yes. Okay. Quest failed. What? Maybe there's no such thing. Huh. So I guess I would need to basically take those 3 models and can I search for this specific model? Okay. Average speed is medium, price is this. Only text input and output. Text is small is our improved, more performant version of our ADA embedding model. Look at that. Embeddings are a numerical representation of text that can be used to measure the relatedness between 2 pieces of text. Okay, so I want details. So this is real cheap. Yeah, it has batch endpoint, so that's nice. No fine tuning, no other stuff. We don't care. Rate limits, whatnot, whatever. Um, that doesn't say anything. Batch API price is even lower. Wow. Holy moly. Okay. So how do I get more info? Do I need to go into their stuff? I guess. Let me just do. I'm gonna try something. Let me just create a new project and we're gonna call it live stream create. All right. So we're on live stream on this thing. And can I go to like playground? So I want model is small. Ooh, nothing. Seriously. Reasoning. Other prompts, images, assistant, TTS. Huh. They don't even. Oh, what a joke. API reference. Oh well. What's going on here? So, absolutely right to question this approach. Here's my analysis. The trade off of single article embeddings. Why 1536 dimension vectors might be overkill for whole articles. They might be overkill? Really? Information compression, when you embed an entire Wikipedia article, potentially thousands of words, into a single, you know, this kind of vector, you're compressing a lot of diverse information into one representation. This can lead to loss of nuanced details, averaging effect where specific facts get diluted, difficulty matching specific queries to specific sections. In token limits, the text embedding 882 has 8,191 token limit. Okay. Simple English Wikipedia articles are shorter but still substantial. Okay, that's good to know. We got some information that wasn't specified in their docs. Benefits of chunking, better precision, smaller chunks, paragraphs or sections could create more focused embeddings that better represent specific topics. For retrieval, user queries often target specific information rather than entire article themes. Exactly. And dimension efficiency, you're right. With chunking, you could potentially use smaller embedding models like 384 or 768 and still maintain quality. So why OpenAI might have chosen all article embeddings? Simplicity, simple English Wikipedia, much shorter. Demo purpose and storage trade-off. One embedding per article versus proportionally 10, 20 chunks per article. Okay, my opinion for production RAG system, chunking would likely be superior. Okay. The current approach works for simple English Wikipedia because articles are concise. Yeah. Okay. So it is situational. All right. So now the question is, let's see if, because we can get any information here. Can I get back to, come on, back. There you go. There's the list. I'm having trouble finding info about the whatever input limits and produced dimension for these models. And let's just paste it and kind of clean it up. And this one. There we go. Let's see if it can give us something. I'll search for stuff. Why not? I'm kind of scattered around right now, but I want to just have an idea of what those things are. Because it's so cheap that it might be just, you know what, screw self-hosting. If this is gonna cost me $1 a month to run, I don't care. Limit. Okay. Alright, this is gonna take a while. But after that, I think I'm gonna be heading towards finish line. But for now, I can imagine that, you know, we get the input article, right? We got an article as input. Then we basically send it to whatever, split it into chunk 1, right? Chunk 2 and chunk 3, let's say. So we can just do bam. So that will be basically our sentence-based chunking. So that's the goal here, right? Let's make it like this. Fancy. So then, after we have this done, we can basically send them over into making embedding 1, embedding 2, and embedding 3. So again, we have like, you know, so this will be suddenly generate embeddings via AI model. And yeah, there we go. So we do that, and we end up with this, right? So then next step will be, okay, so now what we're gonna do is article in DB. Okay, and maybe it will have something like title embedding that will be just included in it. And then we have a separate thing, which will be those three that basically point to it, right? They kind of point at it that, hey, we exist in a database, so great. So we could have basically a table called contents, whatever. Okay, and then we have embeddings table, right? Could even make it like content embeddings table. There we go. And we can actually do title. And this doesn't use the chunking, right? Then title embedding. I'm making it now because this will be for reference later. And then suddenly all this, we can just say, hey, this thing now goes and will be save in DB. And then retrieval, like searching for an article, will be like, hey, we're searching, it'll be search the title and through all the embeddings for that customer. And that's pretty much it. And then it basically, whatever embeddings we find for articles, how many embeddings we can probably add their strength towards an article and do some stuff, some simple math and just find stuff. Okay. So this is the whole idea how to do it, and all that needs to happen per article, and somebody might be uploading like 200, 300, 5,000 of them at once, so there will need to be an entire system that kind of queues them up, so we're not doing too much at once. All right, I can deal with that. And this is, yes, always fetch stuff from internet, please. That was fast. Opus 4 limit reached already? I guess that's a very small limit for Opus 4, because this is not a lot of tokens. Okay, so 88.2, yes, exactly. 1536, token limit, most widely adopted baseline performance, moderate pricing, right? The three smalls also creates 1536 dimensions. Wow, can be shortened to 512. All right. Token limit, most cost effective of the V3 models, better performance, and supports Matryoshka representation learning, whatever that means. Okay. I mean, 10 times lower than, 5 times lower than Ada. Yeah. And text embedding 3, large. Wow, that's a lot more dimensions. Can be shortened to, oh wow, so many options here. Wow. Features best performing model, supports MRL, and maintain performance at reduced dimensions, and 256 dimensional version outperforms Ada at full dimensions. Wow. Higher than other models due to large dimensions. Okay. Interesting. For a chunking question, the newer model's ability to maintain performance at lower dimensions actually supports your argument. You could chunk articles and use smaller, more efficient embedding without sacrificing quality. Okay, that makes me excited. That's fun part. I like that. Okay. All right. I can do that. Okay, so that'll be it for tonight. I personally learned a lot, both about full text search and about the vector search even more. Some syntax is still confusing, but we got to the point where we understand something about chunking. There are good tools for that. We understand things about, okay, how we generate those embeddings, just send it to the model, we can self-host or whatnot. and then we can just store stuff in tables and whatnot, and just uh, be smart about retrieval. And yeah, with those multiple embeddings, sure, it adds complexity, but at the same time, I feel like one can really, especially with smaller embeddings, one could really make it accurate and I guess fast. Another question will be, how does the performance differ if we have high dimensional embeddings comparison? Like, let's say we have, I don't know, 50,000 embeddings that are, uh, what is it, 1536 dimensions, right? Versus maybe 3 times as many, but of 512, right? Where the search would be, when the search would be actually faster? That's the question. Yeah. All right. So that will be it for me. Thank you for watching. I hope you learned something too. And I'll see you some other time. I don't have any specific schedule right now. So we'll see how it goes. But I know that I will be most likely making it all open source. Probably in .NET out of all the languages. So we'll see how it goes. All right. So thank you for watching. Have a great day or night or whatever it is. And see you around.